Hi everyone. So let's start. Now we will talk about the eigenvalues and eigenvectors, right? Okay. So let's ask a question that what happens when a matrix hits a vector, which means if there is a vector x and let's suppose 1 3 and there is a matrix which is let's suppose a which is 1 2 2 1 any random matrix. If I multiply this vector x with a matrix a, which means like matrix is hitting a vector, then what's going to happen? So there are two possibilities. One possibility is that vector get rotated and scaled. So which means like if you started with the vector x, which is 1 3, and if you multiply with this vector with a, which means ax, now ax is coming out to be 7 5 in this case, then then this ax, which is like 7 5, has got rotated, and maybe this length might also have got changed, which means like it got also scaled, right? So x was this and ax is this. This is one possibility, which means like x was this and x got rotated by some angle and then also scaled, right? This is one possibility. Another possibility is that, like, can anyone tell me what could be another possibility? So if you're multiplying a vector with a matrix, then what may happen? One is that like it may get rotated and it may get scaled. So scale, reverse means scale, like both are same. So it may get rotated and with some angle. So reverse means if you are saying the changing the direction also, it covers the possibility one covers this. So another possibility is that it doesn't get rotated but only get scaled. Okay. So another possibility is that vector gets only scaled, which means if this is a vector x and suppose this was a matrix and the vector in this case is let's suppose x11, then this ax is just 3 3 and then this is just getting scaled by the factor of 3, right? So earlier vector was I think 1 3, that 1 3 vector got scaled, got rotated and maybe scaled, but this time vector is 1 1 and this vector got only scaled, it hasn't got rotated. So these kind of vectors are called eigenvectors. Okay. Let me go in the more detail, like what are the eigenvectors, and I will tell you the geometric meaning again. So I will come back to this diagram. Okay, this like say almost similar diagram. So like there is a big question that why they are always in limelight, like why they are so popular, like why we are studying this eigenvectors and eigenvalues. Answer is very interesting, but unfortunately I want to be able to tell the details that is like eigenvalues and eigenvectors are extremely important in machine learning, extremely important in machine learning. So in machine learning, like there is concept called regularization. In machine learning, there is a concept that is like, that is basically, I can say that is a basis of any machine learning algorithm. So there is a concept called regularization that is kind of basic, like that has to be there for almost any machine learning algorithm. And to understand the regulation and why it works, like why the regulation works, you need to understand what are the eigenvectors. So the whole theory of regulation is based on the eigenvectors only, right? So like there are many type of regulation in machine learning, and almost every type of like all type of regularization depends on the eigenvectors, like understanding of the eigenvectors. But obviously like we won't be talking about these things, and like the answer of this is very like answer of this is basically like why they are in limelight. It is from machine learning point of view, there's eigenvectors are very important, but obviously we want to be able to talk about these things. But yeah, these are very important. This is very important topic in if you want to know like how things are working in machine learning. Actually, like for many of the machine learning practitioners, like who do machine learning like at the basic level, they might not know the regularization and eigenvector concept, but they are just calling the library and they are just using them. But how things are working behind the scene is basically most of the algorithms in machine learning working with the help of regularization, and which can be understood only with the help of eigenvectors and eigenvalues. Okay, let's go to the geometric meaning. Suppose you have some r2 space here, and you want to multiply every of this vector with some matrix which is 9443, and you transform all of this vector into some other vectors. So let's suppose there is one vector in R2, which is, let's suppose, xy, and if you multiply this xy with this 9443, then I think you will be getting 9x plus 4y. So if you multiply this, then it will be 9x plus 4y plus 4y, and then this will be 4x plus 3y. Okay. And anyway, not just regularization, like there are many concepts. There is a very important concept called dimensionality reduction using principal component analysis in machine learning, that is called PCA, and PCA is entirely based on this eigenvectors only. Like there are many things in machine learning which are dependent on eigenvectors only. Okay. So let's suppose you start with some matrix 9443 and you multiply this matrix with every other vector in your R2. Then in general, if you're multiplying with xy, then you are getting 9x plus 4y and 4x plus 3y, right? You can do it. Now let me take the concrete example. Let's suppose you are taking 0, 0 here, maybe this element 0, 0 here. Now 0, 0 is mapping to 0, 0 only. Okay. 1, 0, this is 1, this is 0, right? This 1, 0 will map to 9, 4. This will map to 9, 4. 9, 4, somewhere here, right? This was 1, 0 here, and this 0, 1, I think x is 0, y is 1, right? So this is 0, 1. So 0, 0, 1 is mapping to 4, 3, somewhere like 4 and 3, maybe somewhere here. Anyway, like these vectors are getting mapped to some different vectors. So I think I have the diagram here. Yeah. So these are the four values, 1, 2, 3, 4, or 5 values, including 0, 0 I have taken. And these 5 values are mapping to these other 5 vectors. Like these 5 vectors I started with, and these are mapping to other 5 vectors, right? Now, do you remember what I told? What are the eigenvectors? Eigenvectors are the vectors corresponding to a matrix A, which if I multiply with the matrix A with that vector, then that vector doesn't change their direction, right? So do you think there is any eigenvector here? Like initially, let's suppose the direction of this vector was this, then maybe this got mapped to 9, 4. This is changing the direction. This is 1 second. Yeah, this is changing the direction, right? So this is changing the direction to here. Initially it was this direction. Now it is changing the direction. So definitely it is not eigenvector. Similarly, this was initially maybe like this was this direction. Now it got changed to this direction. This is not the eigenvector. Now there is no eigenvector, right? And 0, 0, 0, 0 is never considered as eigenvector. So like otherwise, like it is by definition basically like we do not consider 0 vector as eigenvector. Okay, this is by definition basically. Eigenvectors are non-zero vectors. Eigenvalue, like I will talk about it later. Eigenvalues could be zeros, but eigenvectors can't be zeros. Okay. So you started with this circle and you ended up with this ellipse, right? Now let me tell you some vectors here which are not changing their direction. Like these are not 4 vectors. These 4 vectors are changing their direction definitely, but there are some vectors which like vectors are this 2, 1 and -1 and 2, like this direction. This is 2, 1. Okay, this is 2, 1. This is -1 and 2. These two directions we just see, these two directions, this red direction and then this green direction, these two directions are not changing their these two vectors are not changing their direction. It was 2, 1 here. It is maybe like getting scaled with some number, some 11 into it is 22 into 11 here, and this is getting scaled with just 1, 1, -1 and 2. But they are not changing the direction. They may get scaled, may not get scaled, but they are not changing the direction. So these two vectors are called eigenvectors. Okay, eigenvectors. Eigenvectors are the vectors if you multiply this A. So basically, this whole setup is called linear transformation, which is not important for us. But yeah, this is called linear transformation. You take some vector space, you multiply that vector space with some matrix, and you are transforming every vector. This is like this transformation is special, and this is called linear because like basically it holds the property of linear transformation. So you are starting with a circle, and now you are ending up with the ellipse, right? This is the ellipse. And this ellipse major axis, and I think this is called major axis, I think, if I'm not wrong, or minor, I think this is called major axis. So this major axis, minor axis, these are the eigenvector directions. This axis direction, whatever it was here, like here, it was this in this case. So basically these two directions are not changing. The like after multiplication, these two vectors are not changing their directions. So these are called eigenvectors, but they may get scaled, and the magnitude on which they get scaled is called eigenvalue. Okay, it's called eigenvalue. What is 2 into 2 matrix? So 2 into 2, this is a random matrix. There is nothing special about this matrix. This is a random matrix you have taken. Okay, you are applying, you are basically transforming your space, which is R2, with this matrix, and you are seeing what is happening with the other vectors. So here there are two vectors which are not changing the direction. Every other vector, like as we have seen, every other vector is changing their direction to somewhere, right? And these two vectors are called eigenvectors. Yes, eigenvectors are specific to the matrix. So if you take another matrix, then these vectors won't be eigenvectors. There will be something else which will be eigenvectors, right? Okay, like we will go to the formulation, but like I just wanted to tell you the geometric meaning. So this chapter enters a new part of linear algebra based on the Ax equal to lambda x. Now, basically, when I'm saying it doesn't change the direction, it means that I need to write Ax equal to, if it is not changing the direction, it is changing only like getting scale, then lambda x, right? Now the direction of this Ax, is, I mean, Ax is parallel to basically parallel to x, right? That's why I'm able to write Ax equal to lambda x. So that's how they have defined. Like by definition, this is Ax equal to lambda x, which means x. If I say Ax equal to lambda x, which means x is an eigenvector. X is an eigenvector. What is significance? That's what I'm saying. That significance is like, as I said, like these are very much important in machine learning. Like if I tell you very quickly, like I'm just telling very quickly. No, lambda is eigenvalue. So suppose you have some data, okay? Like this is a disclaimer, like you want to be able to understand this, even 10% of it, what I'm going to say, but I'm quickly going to say in 5 minutes. So suppose you have some data, some points you lie here, like let's suppose you have some points, okay? Something like this. So now you are having this data, and there are two, like this data is 2-dimension. Let's suppose this point is 3,4, something like this. So you have some data, and 3, 4, something like this, right? So you have 2-dimensional data. So where you have two entries for every data point, you have two entries. But there is some technique called dimensionality reduction. Like in machine learning, you many of the times you have big data, like you have many features, many coordinates for every single data points. Like this is very much related to, you have some image, and you want to compress this image. Basically you want to represent the same image using the smaller pixels. So let's suppose this is 215 to 500 or something like that. Then you can represent this image using the smaller pixels, and most of the features get retained. So basically instead of just representing this data with the 2-dimension, if I just change my direction like this, if I just change my frame of reference like this, then I can say that, okay, one of my coordinate is almost 0, right? Like one of my coordinate is almost 0, another coordinate is something else. So instead of 2-dimension, I can just say that this is just 1-dimension. My data is just 1-dimension, right? So earlier it was 2-dimension, 3, 4, right? But now if I just change my axis, then I can say it is just 1-dimension data, because other coordinate just 0. Now how to find that direction, right? How to find that direction? It is basically eigenvector direction of covariance matrix. Basically we see that in what direction my data is varying too much. So we find the covariance matrix of this data. Like we will study this in probability, and then based on the covariance matrix, we find the eigenvectors of the covariance matrix. Now the eigenvector which is corresponding to the highest eigenvalue is the direction of direction in which my data is varying too much, and this is the direction I am very much interested in. If I just take this direction, then I'm actually preserving most of my data. So anyway, so Eigenvectors, as I said, like this is helpful in machine learning. Like apart from this dimensionality reduction, this is also helpful in regularization. I think I've written that in earlier slide. So anyway, like eigenvectors are very, very important in machine learning, but it's just like we at this point we will just know that what are the eigenvectors and what are the eigenvalues. That's all. Okay. Covariance matrix we will study in probability. Covariance and variance, these things we will study. These things are in syllabus. Covariance and variance, this we will study. Okay, so eigenvalue is, I'm not representing with the vector. So ax equal to lambda x. Here x is called eigenvector. Eigenvector. And lambda is a scalar, which is called eigenvalue. Okay, lambda is a scalar, which is called eigenvalue, and x is vector, which is called which is called eigenvector if you have ax equal to lambda x. Now the direction of ax, like ax is same as lambda x, so I can say the direction of ax is parallel to x. That's why it is eigenvector. Okay, and eigenvectors, remember, eigenvectors by definition are non-zero vectors. Eigenvalue could be zero, but eigenvectors cannot be zero. Now tell me if you have an identity matrix, let's suppose a 3 by 3 or something. If you have an identity matrix, then this I into x is what? X. X is any random vector, right? Like I have not taken any specific vector. You can take any random vector. You can just say I into x equal to x. You can just take any random vector. So can I say any vector is eigenvector of identity matrix? Can I say any vector is identity matrix, like eigenvector of identity matrix? Yes, I can say, right? Because I'm able to write ax equal to lambda x, then why not? Right? If I'm able to write where a is ix equal to lambda is just 1 into x, which is a scalar. So yes, if I'm able to write ax equal to lambda x, then why I can't say? Yes, I can say, right? Yes. So any vector is an eigenvector for identity matrix. Any non-zero vector. Basically, by definition, these are non-zero. Eigenvectors are non-zero vectors. Okay. Okay. So just tell me if you are convinced with this statement or not. If x is an eigenvector, then any non-zero multiple of x is also eigenvector, which means suppose x is an eigenvector. It is given. It is given. Okay. Now they are saying any multiple of x. Let's suppose kx. A kx. This is a vector, right? This is also a vector. Is this also eigenvector? Tell me. Is this also eigenvector? To prove that this is eigenvector, I need to show that a into this vector, sorry, a into ax, yeah, a into x equal to a into kx equal to lambda or lambda dash, like whatever, like some scalar into kx. This is what I want to show, right? This is what I want to show. Then I can say that yes, this is eigenvector, right? If I am able to show like this, then I can say yes, this is an eigenvector. So since k is a scalar, it doesn't matter whether you write it in between or you write it before a. You can write k anywhere. So it is a into kx. You can just write it like this, k into ax. You can write k anywhere. You can write ax, k. Everything is same. Okay. Since k is a scalar. If it is vector, then obviously you can't permute. But if it is a scalar, you can permute. Like you can write in any way. So you can say that this is k into ax, and then you can say that yeah, this is lambda. Ax is lambda x, right? Ax is lambda x because x is eigenvector. So you can say this is like this. So what you want to write like this, lambda into something, lambda into that vector kx. So you can write like this, yes, lambda into. Is this okay to everyone? So if x is an eigenvector, then any multiple of x is also eigenvector. Okay. Then what is the eigenvalue of that multiple? So if x is an eigenvector of eigenvalue lambda, then then what is the eigenvalue of kx? It is same, right? Which is lambda. because lambda into x so lambda into x, and here you have lambda, so that's why. No, Ananya, as I said, lambda is never like lambda. The way I'm using the notation, lambda is scalar, which is eigenvalue. X is vector, which is eigenvector, right? So, okay, let me do it slowly. So, ax equal to lambda x. If I write ax equal to lambda x, the way I'm representing it, x is a vector, which is eigenvector. Okay, and lambda is scalar, which is called eigenvalue. Okay. Now, let's just multiply both sides with k. It will be a kx, right? If you multiply both sides with k, then on the right side it will be lambda into k into x. So you can just write lambda kx, right? If you multiply both sides with k, is this okay to everyone? Multiplying both sides with k. So what I'm doing here? Both sides with k. Okay. So what can you say from this equation? What can you say from this equation? If I'm saying a into some vector which is kx equal to lambda into a into some vector which is kx equal to, I'm saying lambda into the same vector kx, then what can you say? That kx is also eigenvector, right? With eigenvalue as lambda. Okay, kx is eigenvector with eigenvalue of lambda. This is what I want to say. Okay. Now eigenvectors, again, like in this chapter, like we will only talk about the square matrices. But just to tell you that eigenvector only makes sense for the square matrix. Why? Because you want to have ax equal to lambda x. But if you do not have a square matrix, let's suppose you have m cross n matrix, then this is n cross 1, then it will be m cross 1. So you can't have lambda x, right? So I mean, you can't have this same vector. You can't have this vector as same vector, this x prime, right? Because this vector, like, see, ax equal to lambda x, you want this vector and this vector is same. But if this is not a square matrix, if this is not a square matrix, then this vector will be having n cross 1 dimension, and this vector will be having m cross 1 dimension, right? So this cannot be same, right? Yes, Digvijay, you can say this. So each eigenvalue corresponds to infinitely eigenvectors. That's true. But interesting thing is that, are those vectors linearly independent or not? That's what we will answer today. Okay. So so basically from this x is eigenvector, lambda is eigenvalue. So for lambda eigenvalue, x is eigenvector, kx is also eigenvector. But for lambda eigenvalue, x is eigenvector, like 2x, 3x, like everything is eigenvector, right? 2x, 3x, these things are eigenvectors. But are those linearly dependent or independent? So in this case, they are linearly dependent. But can we have linearly independent also, right? So this is very easy to see that they are linearly dependent vectors, x, 2x, 3x. But do we also have linearly independent vector corresponding to the same eigenvalue? This is what we will see. Okay. In my question clear, like what I'm saying to everyone? So see, for lambda, for this lambda, you have kx as an eigenvector, right? Which means for this lambda, you have x, 2x, 3x, everything is eigenvector. 4x, everything is eigenvector. But are those eigenvectors linearly dependent or independent? So like in this case, these are linearly dependent. But can we also have a case where these eigenvectors corresponding to the same lambda are linearly independent? We will see this. Okay. So let's go to the formulation that we have ax equal to lambda x, right? Where this x is eigenvector, again lambda is eigenvalue. This is scalar. Let me just read out what I have, what is written here. The eigenvalue lambda tells whether the special vector x is stretched or shrunk or reversed or left unchanged, right? So suppose lambda equal to 1, then tell me, is this x has shrinked or scaled or what, or left unchanged? It is left unchanged, right? If it is -1, then reverse. If it is again 2, then stretch. If it is 1/2, then shrunk. Right? And if it is, let's suppose, -1/2, then reverse and shrunk, something like that, right? So this lambda will tell you that whether it is reverse, shrunk, or like that, right? Left unchanged means like you started with x. If lambda is 1, you started with x. You started with x. If lambda is 1, then you are getting 1 into x, which means you are again getting x. See here. Here, I think the one of the eigenvalue is 1, right? So if you started with -1, 2. If you are multiplying 9443 with -1, 2, you can do it. 9443 with -1 and 2, you will be getting -1, 2 only, which means you multiply this vector with this matrix, you are not going to, this matrix is not going to change. This is not going to change, right? This matrix is not, this vector is not going to change. We get only lambda for each ax, only one lambda for each ax. How do you take? No, for each ax, see here. Okay, let me go to the next page maybe. See, ax equal to lambda x I have, right? Now we will see like how to solve it. Suppose there is one lambda. Corresponding to that, I'm saying that how many eigenvectors you have. The lambda is fixed, eigenvalue is fixed, this is fixed. Now I'm saying that if x is an eigenvector, then if you multiply with the k both sides, you are going to have akx. You can also say corresponding to the same lambda, kx is also eigenvector, right? Corresponding to the same lambda, if x is eigenvector, then kx is also eigenvector. See, what is the definition of eigenvector? Eigenvector, if you multiply any vector with a, right? If you have lambda into the same vector, then this vector is eigenvector. So corresponding to lambda, x is eigenvector, kx is also eigenvector, which means like 2x is also eigenvector, 3x is also eigenvector, like that, right? See here, if you have identity matrix, then corresponding to lambda equal to 1, you have ix, like whatever x you can take, 2, 3, like whatever x. You know, this is also eigenvector, 2, 3 is also eigenvector, 4, 5 is also eigenvector. In this case, these are independent, right? 4, 5, and 2, 3, these are independent. But in this case, is x, 2x, 3x, these are dependent. So sometimes dependent, sometimes independent. I mean, corresponding to one eigenvalue, you can have multiple eigenvectors, obviously. But sometimes those eigenvectors are dependent, sometimes those eigenvectors are independent. Okay. So I will talk about it later. But for now, you just need to understand that if x is eigenvector corresponding to lambda, then kx is also eigenvector corresponding to lambda. Okay, where k is some non-zero. Okay. Okay. So how to calculate those eigenvectors? So till now we have a little bit understood that what is the geometric meaning of these eigenvalues and eigenvectors. Now let's first understand that how to calculate those eigenvectors. See, again, I'm saying that eigenvectors are non-zero vectors. Okay, eigenvectors are non-zero vectors. Now, ax equal to lambda x is clear to everyone, where x is eigenvector, lambda is eigenvalue. Lambda is obviously scalar, x is vector. You can rewrite it ax minus lambda x equal to 0. You can again rewrite it a minus lambda I into x equal to 0. Now tell me, do you remember from ax equal to 0, system of homogeneous solution? If I say, okay, let me just see if you are able to recall. If I say that this has non-trivial solution, means x is not 0, basically I'm saying x is not equal to 0. What can I say about the columns of A? What can I say about the columns of A? Dependent, independent, something like this. They're dependent, right? Because linear combination of columns of A is giving you 0, right? This means the linear combination of columns of A is giving you 0, which means rank of A is less than n, right? I mean, there are lesser pivots than n. So anyway, so basically if rank of A is less than n, or the columns of the matrix is linearly dependent, then you can also say in terms of determinant. So determinant of A. So here, from here, you can also say that determinant of A is 0. So basically, if, let me just write it like this here, if rank of A, where A is, let's say n cross n matrix, okay, is less than n, then columns of A are linearly dependent, right? This also means that Ax equal to 0 has non-trivial solution. Okay. This also means basically, this also means that determinant of A is 0. Okay. Where, like, this is possible only when rank of A is less than n. Basically, if you have linearly dependent columns, then determinant of A is 0 or rank of A is less than n. Okay. If you have linearly dependent columns. So if you just go back to this, if I am saying that this has non-trivial solution, which means like eigenvector, this x is not 0, x is non-zero, then what can you say about determinant of A minus lambda I? No, determinant of A is 0 is not by definition. So basically, can anyone tell me why determinant of A is 0? Can anyone tell me why determinant of A should be 0? If A is n minus n, yes, at least one row 0. Yes, Sandeep, very nice. So see here, if like in this case, you have, if rank of A is less than n, in this case, you have free variables, right? Free variable, right? Since you have free variable across, like, see, this is n cross n matrix. So if you have free variable, then this will be 0. Like at least one row or one column will be 0. So basically, one row or one column is 0, which means determinant of A is 0. So basically, like we can convert, given A, we can convert, like we want to find the determinant of A. Okay, we want to find determinant of A. Then we can convert this A to row reduced form. Sorry, not reduced, like row echelon form is enough. Echelon form, right? Form without, this is important, without changing determinant of A, right? I mean, you may change sign, but let's not worry about the sign. So you may change sign if you are having the elementary row operation, which is swapping the rows. You may change sign, but without changing at least the magnitude, you can do it, right? You can change given A to row echelon form without changing the sign. So if the rank of A is basically less than n, or if you have linearly dependent columns or linearly dependent rows, then there will be at least one row with all the zeros, and you are able to come from A to this matrix without changing the determinant of A, and then you are saying that this determinant is 0, right? So basically, this is important. Like you are converting to row echelon form without changing the determinant. This is important. You're not changing the determinant, right? I mean, elementary row operation, apart from like changing the sign, if I only talk about the magnitude, like absolute value. So elementary row operations doesn't change the magnitude, absolute value of the determinant, at least, right? So what are the row operations that doesn't change? Which is Ri gives Ri plus Krj. But if you have something like this, like Ri gives K1 Ri plus K2, something like this, then it will change, right? It will change. So it is like, don't do this when you are finding the determinant. You can do this when you are finding the determinant, but don't do K1 into Ri or something like this. So always prefer this. So you can use this rule to convert any of the matrix to row echelon or row reduced echelon, anything, right? So you can prefer this. Okay. So what can you say about the determinant of this matrix? If I'm saying that this has the non-trivial solution, which means the columns of this are linearly dependent or rank is less than n or something like this. So what can you say about this determinant? This should be 0, right? See, I'm why this is zero? Why this is zero? Because eigenvectors are non-zero. Okay, if eigenvectors are allowed to be zero, I mean, if I'm allowed to be zero, then I cannot say that this is zero, right? I cannot, if I'm allowed to take the trivial solution, which is the eigenvector having zero, then I cannot say this is zero. So basically, eigenvectors are non-zero vectors. Then only like these things make sense. If eigenvectors are zero vectors, then you can't say that a minus lambda is determinant is zero, right? Okay, so always remember this. Okay, let me just write in the bracket. But eigenvalues could be zero. Okay, eigenvalues could be anything. Eigenvectors are non-zero, but eigenvalues could be zero. Let me know if there is any understanding issue with this equation. So I hope you got it. We started with ax equal to lambda x. That is very easy. And then from here, I'm just saying that rewrite it like this: ax minus lambda x equal to 0. Then I'm again saying that you can just rewrite it like this: a minus lambda I into x. This is a matrix. This is a matrix or a vector, doesn't matter. I mean, if I'm taking multiplying this, then this is just like another matrix which is just having one row, one column, which is 0. And if I'm having this kind of formulation, which is ax equal to 0, and I'm saying that this has the non-trivial solution. I'm saying that this has the non-trivial solution. Okay, has non-trivial solution, which means determinant of a minus lambda I should be 0. Okay. This is called characteristics equation or characteristics polynomial, but these names doesn't matter. Like we have in the next slide, but these names doesn't matter much. Okay, yeah, characteristics equation. So this is nothing but the determinant of a minus lambda I 0. Now, given this equation ax equal to lambda x, we want to find out two things. One is eigenvalue. Another thing is eigenvector. Okay, these are the two things we want to find out: eigenvalues and eigenvectors. Now, eigen, like using this equation, we will go actually step by step, and using this equation, we will first find out the eigenvalues, and corresponding to the eigenvalue, we will go for the eigenvectors. Okay, so we will first find out the eigenvalue, and corresponding to every eigenvalue, we will find out the eigenvectors. So let's just solve this. Now, in summary, this is the screenshot I have taken from the book. So compute the determinant and find the root of this determinant. And okay, let's just do this. Okay, before I solve any numerical question, just tell me, do a minus lambda I, this is a matrix. Okay, this is a matrix. A minus lambda I is a matrix, and x is again a vector. So a minus lambda x equal to 0 only have the trivial solution. Okay, so basically suppose like my question is something like this. Suppose you find out some lambda, and you are saying that you came up with some matrix a minus lambda I, and you are multiplying with some vector x and equal to 0. Then you are saying, then suppose you are allowed, so suppose you are allowed to take the trivial solutions. Then tell me, does this only have the trivial solution? See, I think I'm confusing you. See here what I said. Sorry. Here what I said, like this doesn't, like eigenvectors can't be 0. This is true, right? Eigenvectors can't be 0. That's why I'm saying this a minus lambda I determinant should be 0, right? Because eigenvectors can't be 0. Now suppose I find out some lambda, and I'm doing a minus lambda I. Okay, and then I'm multiplying with some vector x equal to 0. Now, like just for a question, I'm saying this is not eigenvector. This time I'm not treating this as an eigenvector. Okay, this is some random vector which is allowed to take value 0. This is not eigenvector. Okay, so basically my question is this, that here this time I'm just saying that this is not like need not to be eigenvector. Basically, need not to be eigenvector. Okay, this is not eigenvector, need not to be eigenvector. This is some random vector which is allowed to take some 0 values. Now tell me, this a minus lambda I into x, which x can take 0, then yeah, x equal to 0 is one solution. I'm again saying this is not eigenvector. Okay, x is not eigenvector. X equal to 0 is one solution. Do I have another solutions also? This is what I mean to say. This is what I want to ask. Do I have another solutions also? See, by construction, the way I have made this a minus lambda I made like the way I have found this lambda is by making a minus lambda to be 0, which means the columns of a minus lambda have to be dependent. If the columns of a minus lambda are dependent, then there has to be some non-zero x also, right? So basically, like this question is not useful also, like not much. I don't know if it is much useful, but see what I'm saying, that if you have a minus, the way you made it, the way you made it a minus lambda, you made sure that this a minus lambda determinant is 0. That's how you found out the lambda, right? That's how you find out the lambda. And now I'm asking you, this a minus lambda into x, is this having a non-trivial solution or not? Then it has to have the non-trivial solution, because a minus lambda is 0 by construction, right? The way you have constructed this matrix, this a minus lambda has to be 0, right? Determinant has to be 0. That's why you can say that rank of this has to be less than n. That's why you can say that it has to have the non-trivial solution. A is a matrix, but if x is 0, 2, yes, non-trivial, 2 possible. No, Ananya, x is 0 is one case. If I'm saying that if x is not 0, is it possible that x is not 0 and still you have solution? So yes, if a minus lambda determinant is 0, so if a minus lambda determinant is 0, like by construction we have made this matrix in such a way that a minus lambda determinant 0, then x non-zero is also possible, right? Okay. But x is not treated as eigenvector, no need for determinant. So that's what I'm saying, Sandeep. Like once you found out the eigenvalues, like now you found out some lambda. Okay, this is the eigenvalue. I agree. This is the eigenvalue. But let's not worry. What is this? Like let's forget what is eigenvector, what is eigenvalue. Let's just talk about the simple equation ax equal to 0, where a is your a minus lambda. Okay. Lambda you found from eigenvalues. That's okay. Lambda you found from eigenvalues, but this a minus lambda into x, I'm talking about this equation, this set of linear equations. So this set of linear equation has to have some non-zero solution, because the determinant of this a minus lambda is 0. The way you have found out the lambda earlier and then you have put the lambda here, then you have constructed this a minus lambda matrix in such a way that determinant is 0, right? Yes, yes. Okay. Okay. Before I go to some theorems which are important, let me just take one simple example and let's just find out the eigenvalues and eigenvectors. Once Anand is saying x could be non-zero for eigenvector. X should be non-zero. Why you do? Yes, that's what I'm saying. Like I just asked a random question. I mean, this. Let me ask a question in different way. Instead of a minus lambda, let me just ask like this: ax equal to 0. Let's just say x equal to 0 is given, and determinant of a equal to 0 is also given. Then tell if non-trivial solution is possible or not. This is the question, which means like this is given and this is also given, and determinant of h 0, that is also given. Then they are asking whether non-trivial solution is possible or not. See, ax equal to 0, like for this equation, if determinant is 0, which means rank has to be less than n. Okay, A is n by n matrix, let's suppose. Rank has to be less than n. If rank is less than n, then what can you say about the solutions of x equal to 0? Then this A is having linearly dependent columns, which means this C1 and like this X is, let's suppose C1, C2, C3, C1 the first column A1 plus C2 A2 plus C3 A3, this is 0, where one of the CI is non-zero, right? One of the CI is non-zero, which means like they're linearly independent, which means like this X or this X is like X could be a non-zero vector, because one of the CI, which is like which is a component of X, so it is non-zero, that's why X is non-zero. What if rank is 0? Rank is 0 only when this is null matrix, like if every other element is 0. Okay, let's do some questions, some numerical questions to find the determinant, to find the eigenvalues and eigenvectors. Can you give me some example? 1, 2, maybe 1, 3. Amar, we can discuss it later if there is some confusion. 2, 3, 5, 4, 1. Okay, I have taken some example. So let's suppose A is this, and if you find out, like you want to find out the eigenvalues and eigenvectors of A. Okay. So what you need to do, you just need to say Ax equal to lambda x. You do not need to write it again and again. Like you can just find out A minus lambda I, determinant 0. Okay. So what is A minus lambda I? You can just do it. A 1 minus lambda, 2, 1, 3, 2 minus lambda, 3, 5, 4, 1 minus lambda. Okay. Just to simplify, let me take this 0 so that I do not have much of problem. Okay. So can you find the determinant of this? It will be 1 minus lambda into 2 minus lambda into 1 minus lambda minus 12, right? This is plus, this is minus, this is plus, and then plus 1 into 5 into 2 minus lambda minus 12, right, equal to 0. So yes, we can do the row operations also. If row operation is giving you a simpler form, you can always do for the determinant, you can do this row operation for any determinant, right? But yeah, okay, very careful. You can do it for determinant only. You can't do it for matrix. I mean, you can't apply the row operation on the matrix and then subtract the lambda, right? Once you have the determinant form, you can do it with the lambda, you can do it, but without the lambda, I mean, without subtracting it with the lambda, like you, if you think that you can do the row operation first and then you can subtract the lambda, this is not possible. Okay. I mean, in that, like, very simple rule is that with the determinant, you can do any row operation you want. But in the matrix, this doesn't make any sense. Like in the linear equations, it makes sense, but in the matrix, you can't do row operation and then you can't subtract with the lambda. It will be wrong. It will be completely wrong. It will give you a wrong answer. Okay. So anyway, you can solve this and you can find the value of lambda, and based on the lambda, you can find the value of the eigenvector. So I think I have the examples in the next slides, but you can take it as a homework. Okay. You can try to do it. I know none of you will do it, but yes, I will still, I'm still saying that you can take it as a homework, and I have the examples in the next slide, so that's why I'm skipping. Okay, calculating the value of lambda. So I hope you know how to do it. Like you can find out the value of lambda. For every lambda, you can find out the value of x. Okay, we will do it in the next slides. Yeah, let's do one of the very interesting theorem, which says that prove that eigenvectors from the different eigenvalues are linearly independent. Which means, suppose there are two eigenvalues, lambda 1 and lambda 2, and lambda 1 is not equal to lambda 2. Okay, different eigenvalues. Now there is one eigenvector E1, there is one eigenvector E2. What they want to prove that E1 and E2, if that's the case, which is given, which means like lambda 1 is not equal to lambda 2, that is given, then they want to prove that E1 and E2, which are correspondingly eigenvectors of lambda 1 and lambda 2, then they want to prove that E1 and E2 are linearly independent. Which means that if I just say C1 E1 plus C2 E2 equal to 0 is not possible. This is what linear independent means, right? Are you able to recall? Linearly dependent means equal to 0. Linear independent means is equal to 0 is not possible basically. Or if it is possible, so basically I mean C1 E1 plus C2 E2 equal to 0. If it is possible, then only possible, yes, possible only when all CIs are 0, right? So this is what you want to prove. This is possible only when all CIs are 0. Okay, let's just do this. Let's take it as equation 1. Okay, I will show you that this is possible only when all CIs are zeros. Let me take it as equation 1 or equation A. Let me multiply this equation A or equation 1. Let me just take, because A is a matrix name, no? That's why let's have different equation name. So let's just take it as equation 1. Okay, so let me multiply this equation 1 with our matrix A. Okay, then what you will be getting? You will be getting C1 AE1 plus C2 AE2 equal to 0. Let me know if there is any problem how we have started. See, we have started with the argument saying that C1 E1 plus C2 equal to 0 is possible. Like we want to prove this is possible only when all CIs are 0. This is what we want to prove, right? This is what we want to prove. So we have assumed that this is true, and let's see like what's going to happen. Are we able to come up with C1 like all? Are we able to come up with the argument then when all CIs are zeros? Okay, let's just see. So what I'm doing, I'm multiplying this this equation with the matrix A, and then I got this equation. Now tell me, can I write this C1 lambda 1 E1, because E1 is an eigenvector, right? E1 is an eigenvector corresponding to lambda 1. That's why I can write AE1 equal to lambda 1 E1, right? Similarly, AE2 equal to lambda 2 E2. Is this okay to everyone? Because E1 and E2 are eigenvectors corresponding to lambda 1 and lambda 2, where lambda 1 is not equal to lambda 2. Okay, this is given, and I want to prove this. This is not possible, or this is possible only when all CIs are zeros. So this is C1 plus this is C2 lambda 2 E2 equal to 0, right? So this is basically one way of doing it. Like I can multiply with the A. Sorry, and another way of doing it like this. So I started with this equation. I'm multiplying this equation 1 with lambda 1 or lambda 2, anything. So let me just multiply with the lambda 1. Okay, since lambda and E can't be 0, so she should be 0. 1 second. So you just multiply with the lambda 1. It will be C1 lambda 1 E1, C1 lambda 1 E1 plus C2 lambda 2 E2, right? Which is 0. Now this is one equation I got. If I multiply with capital A, which is matrix, this is another equation I got if I multiply with the lambda 1. Are both of the equation fine to everyone? So we started with this equation. We multiply this equation with capital A first and lambda 1. So we started with some equation, right? We multiply with A, we multiply with the lambda 1. So these are the two multiplication that we have done on the same equation, and we have got two different equations, right? Is this okay to everyone? Now, just by observing these two equations, what can you say? See, C1 lambda 1 is common to both of them. So I think if you just subtract both of this, then you will be getting C2 lambda 2 E2. Okay, one thing is wrong here. I multiply with the lambda 1, right? So it should be lambda 1. It should be lambda 1. Okay. Yes, Sandeep, that's right. So C2 lambda 2 E2 minus C2 lambda 1 E2, right? Should be 0 if I subtract both of them. So now from here, what can you say? C2 E2 lambda 2 minus lambda 1 is 0, right? This is what can you say. Now lambda 1 and lambda 2 is not 0. I mean lambda 1 and lambda 2 are not equal. So this cannot be 0. You can send it to 0, right? See here. You got this. Can you send this term to 0 or not? This depends whether this term is 0 or not. If this term is 0, you can't divide 0 by both sides. If this term is not 0, yes, you can send, right? So you got C2 E2 equal to 0, right? You can send this to 0 because lambda 1 is not equal to lambda 2, which means lambda 1 minus lambda 2, lambda 2 minus lambda 1 is not 0, right? That's why you can send this term to 0. Now you got C2 equal to 0. Now tell me, is E2 0? Is E2 0? Can E2 be 0? No, right? E2 is eigenvector. E2 is eigenvector. Remember, E2 is eigenvector. So eigenvector cannot be 0. Since this is not 0 and C2 E2 is 0, so the only possibility is that C2 is equal to 0. Right? Only possibility. Okay. See, these proofs are little tricky in the sense, like to be very honest, I just remember it. Okay. I mean, and most of my friends are also just remember this proof. Like this proof is little, I mean, obvious after the masters. So like this is very common result that we use in machine learning, that for different eigenvalues, the eigenvectors are linearly independent. And how to prove it? Like we just subconsciously remember it. I mean, like there is no way like I can justify like why to multiply with a and then why to multiply with the lambda one. Okay, so I just remember it that I'm multiplying with the a and I'm multiplying with the lambda one. So like there are 1-2 proofs that I will show you, and there's like I just remember those proofs. So like it's not like I cannot tell you the way. It's like that's how it got proved. Like there is no book or no place in which they will justify like why you are doing this. So they will just say that okay, you multiply this, and then they will show you that C2 equal to 0. This is the only possibility. Similarly, if you multiply with the lambda 2 here, then you will come up with the C1 equal to 0 is the only possibility. So basically, you can prove that C1 and C2 has to be 0. C1 and C2 has to be 0. You can prove this. This means that this C1 E1 plus C2 E2 has only one solution, which is C1 equal to 0, C2 equal to 0. This means what? If this has only one solution, which is this means what? E1 and E2 are linearly independent. Anyway, you do not need to remember the proof. You just need to remember this statement, which is that I will just re-show you the proof. I will prove it again. Like I will just go through that proof again. But you just need to remember that eigenvectors corresponds to different eigenvalues are linearly independent. Okay, this is very important. If I tell you that see lambda equal to 2 and lambda equal to 3, there are two eigenvalues I got from this matrix A, let's suppose. Then whatever eigenvector I got from here, maybe x, okay, or maybe kx. If x is eigenvector, then kx is also eigenvector, right? So whatever eigenvector I got here, maybe y, maybe k2y, something like that. Then this k1x or x or k2y or y, these are linearly independent because they are corresponding to different eigenvalues. Okay. So eigenvectors correspond to different eigenvalues are linearly independent. That's what you need to remember. I mean, if you remember, that's good. I have not seen in GATE whether they have asked this or not, but this is very important. Okay, eigenvectors correspond to different eigenvalues are linearly independent. Okay, here I've written dependent. One second. Oh, sorry. This is independent, right? Okay. So eigenvectors from the different eigenvalues are linearly independent. If you want to prove it, then let's just do it again. Very easy, actually. So you want to show that C1 E1 plus C2 E2 equal to 0 has only one solution, which is C1 equal to 0 and C2 equal to 0. That's the only one solution for this, right? Where lambda 1 is not equal to lambda 2, and E1 is the eigenvector corresponding to lambda 1, E2 is the eigenvector corresponding to lambda 2. Okay. So what you can do, you can just do two multiplications on this equation. You can just multiply this equation with A, you can just multiply with lambda 1 and maybe with the lambda 2. Okay, let me do the three multiplications with the lambda 2. Okay, if you multiply with the A, then you will be getting C1 A1 plus C2 A2 equal to 0. From here you can say C1 lambda 1 E1 plus C2 lambda 2 E2 equal to 0. If you multiply with the lambda 1, this will be C1 lambda 1 E1 plus C2 lambda 1 E2 equal to 0. If you multiply with the lambda 2, it will be C1 lambda 2 E1 plus C2 lambda 2 E2 equal to 0, right? and all of, like, if all of this has to be true simultaneously, then you can say that C1 equal to 0 and C2 equal to 0. Okay. Anyway, so this is the proof of this. If you want to prove that for different eigenvalues lambda 1, lambda 2, for different eigenvalues lambda 1, lambda 2, E1 and E2 are linearly independent. Lambda 1 is not equal to lambda 2 are linearly independent. Okay, they cannot be linearly dependent for different eigenvalues. This is very important. Now let's just go to one more proof. Like, we have one or two theorems in the eigenvalues and eigenvector. Let's just go to both of them. So before I go to those proofs, I will just show you some numerical examples, and for that, like, we will find the eigenvalues and eigenvectors. Okay. So basically, when we are finding the eigenvalues, then it may possible that we have the repeating eigenvalues, which means, like, if you are solving a minus lambda equal to 0, if you are solving like this equation, then this will be equation something lambda cube minus lambda square, some equation, right? Some polynomial in lambda. Then you may end up getting lambda minus 2 whole square into lambda minus 1 equal to 0. So basically, lambda equal to, you just have, this was a 3-degree polynomial, but how many roots you have? Lambda equal to 2 and lambda equal to 1, right? How many roots you have? Only 2 roots. But it was 3-degree polynomial. And this is 2 roots, and this is called repeating 2 times. So basically 2 is getting repeated 2 times, because this is lambda minus 2 whole square. Lambda minus 2 into lambda minus 1, like that, right? So 2 is getting repeated 2 times. So basically, if you are finding the eigenvalues, then it may possible that you may have only less than n, like less than n eigenvalues, right? I mean, if this is 3-degree, then you may have only 2 eigenvalues, or you may have 3 eigenvalues, right? Can you have more than 3? If this is 3-degree polynomial, can you have more than 3? No, right? You cannot have more than 3. Lambda cannot be more than 3. So basically, if this is age n by n matrix, then this polynomial will be of degree n. Okay, we will see with the example, don't worry. If this is degree n, then at most you can have n distinct values. Otherwise you can have repeating values. I mean, less than n values. You can have less than n values. Now if you have 2, let's suppose less than 3 values, which is 2 value, 1 value, you can also have 2 values, 1 values. If you have 2 values, 1 values, then in that case, less than n values, in case of less than n values, then you may have linearly independent eigenvectors, or you may have linearly dependent eigenvectors. So basically, what I mean to say, corresponding to lambda equal to 2, as I like said earlier, so corresponding to 1 lambda, there are many eigenvectors, right? X, 3x, like that, right? So it may happen that these eigenvectors, that whatever I am having, these are linearly dependent or maybe independent. Okay. Okay, I think I'm going too fast. See, if lambda 1 is not equal to lambda 2, in that case, are you sure that are you sure that E1 and E2 are linearly independent? Tell me. Yes. Yes, right? This is what we have proved already, right? We have proved. Okay. Now, this is the case 1. This is case 2. Okay, case 1. Suppose lambda 1 equal to lambda 2. I mean, both eigenvalues are same. I mean, I should not call them lambda 1, lambda 2. This is just one lambda, but let's say lambda 1 equal to lambda 2. Okay. Let's suppose there are 2 eigenvalues, and both are same basically. I mean, you got some equation something like this: lambda minus 2 into lambda minus 1 equal to 0. So lambda 1 is 2, lambda 2 is also 2, like that. Okay, lambda 2 is also 2. So lambda 1 and lambda 2 both are same. In that case, are you sure that E1 and E2 are linearly independent? Tell me. So we are not sure basically. Answer is no. That's okay. Like, we are not sure. But my next question is, can we have, like, can we have sometimes or in some cases, can we have linearly independent E1 and E2? Then answer is yes. Okay, then answer is yes. Basically, we are not sure if lambda 1 and lambda 2 are not same. If lambda 2 if lambda 1 and lambda 2 are not same, then we are sure that they're the corresponding eigenvectors which are E1 and E2. They are not they are linearly independent. We are very sure. Okay, that's what we have already proved. Okay, we have proved it. But if lambda 1 and lambda 2 both are same, then we may or may not have. Okay, we may or may not have. This is what it is saying, that if you have n distinct values like lambda 1, lambda 2, like that, right, lambda n, if you have n distinct values, then obviously you have n independent eigenvectors. This is what we have already proved, right? But if you have repeating values, let's suppose you have only m values, lambda 1 till lambda m, like where m is less than n. I mean, you some values are repeating, which means like lambda minus lambda 1 power 2 or m1 something into lambda minus lambda 2 power m2 something like that equal to 0, right? If some values are repeating, then you can say that you may have, so this is may have n independent eigenvectors or may not have. Okay, may not have. So if you like, if all eigenvalues are distinct, okay, all eigenvalues are distinct. If I say yes, then what we will say, that all eigenvectors are linearly independent. Okay, if I say no, then all then a set of eigenvectors or eigenvectors may or may not linearly independent, right? Eigenvectors may or may not. Okay, this is all I want to say. If you have all distinct, that we have already proved. Okay, this thing we have already proved. But if you have all distinct, then all eigenvectors are linearly independent. But if you do not have, then you can't say that no, like you don't have. If you don't have eigenvalues distinct, then you do not have eigenvectors are dependent, linearly independent. You may have or may not have. Okay, is this okay to everyone? So Sandeep, I will give you example. If lambda is same lambda, then why not only one vector? So Rajan, we will see the examples. Okay, let's go to the examples. Maybe it will clarify the things. Okay, let's take this matrix and let's find out the eigenvalues and eigenvectors of this. Digvijay, like, only thing I'm saying that is this clear? The yes part is clear. Yes part is clear to you. This is what we have proved, right? So this is what we have already proved, that eigenvectors from the different eigenvalues, if lambda 1 and lambda 2 are not same, then E1 and E2 are linearly independent, right? So this is what we have proved. Is this proof clear? Even if this proof is not clear, like at least this statement is clear, that if lambda 1 and lambda 2 are not same, then E1 and E2 are linearly independent. Okay, so corresponding to two different eigenvalues, we have different, like, linearly independent eigenvectors only. Okay, we cannot have linearly dependent eigenvectors. That's what we have proved. So if you have, let's suppose if you have two eigenvectors, maybe lambda, if you have two eigenvalues lambda 1 and lambda 2 which are not equal, then correspondingly eigenvectors E1 and E2, they are always linearly independent. So if I ask you lambda 1 is lambda 1 is not equal to lambda 2, then E1 is corresponding to lambda 1, E2 is corresponding to lambda 2, then are you sure that E1 and E2 are linearly independent? Then you will say yes. Yes, because E1 and E2 we have proved that there has to be, if there are corresponding to distinct eigenvalues, then they has to be linearly independent. Let me know if there is any doubt. And in case 2, if you have lambda 1 equal to lambda 2, then you may or may not have linearly independent. That's what I'm saying. Eigenvectors may or may not be linearly independent. Multiple eigenvectors are also possible for the same value E. No, Digvijay, multiple possible, that's okay. See, lambda 1, for lambda 1 there are multiple possibles, that's okay, right? For lambda 2 there are multiple possible, that's okay. What I'm saying, you pick any E1 from here, you pick any E1 from here, you pick any E2 from here, if lambda 1 is not equal to lambda 2, I'm not comparing among this. I'm not comparing among this. I think you're confused. You're comparing among this x, 2x, 3x, right? I'm not comparing among this. I'm taking E1 from here. I'm taking E2 from there. And then I'm saying that E1 and E2 are linearly independent. Okay. So there are multiple possibles. That's okay. Okay. If there's a confusion. So whatever, like, see here the statement goes like this. If lambda 1 is not equal to lambda 2, E1 is corresponding to lambda 1 and E2 is corresponding to lambda 2. You can take any of the eigenvector corresponding to lambda 1. Maybe this, maybe 3x, maybe x. Maybe here you can take y, maybe 2y, maybe 3y. You can compare x with 3y. No problem. You can compare 3x with 10y or something. Okay. You take any of the E1 from here, any of the E2 from here, and I'm saying that E1 and E2 are linearly independent. Okay. This is what I'm saying. So if lambda 1 and lambda 2 are not equal, you take eigenvector from corresponding to lambda 1, you take eigenvector corresponding to lambda 2, then I can say that these are linearly independent. That's what we have already proved. Okay. See, that's what we have already proved. Prove that eigenvectors from the different eigenvalues are linearly independent. So from the different eigenvalues, lambda 1 and lambda 2, if E1 and E2 are the eigenvectors, then these are linearly independent. Okay. And if they're equal, if lambda 1 and lambda 2 are equal, then I'm saying that may or may not linearly independent. You can't say that they are not linearly independent. They may or may not. Actually, I will show you very specific metrics. For those type of metrics, you always have linearly independent eigenvectors, even though like eigenvalues are repeating. So let's just do with an example. For no case, how many eigenvectors? So Rajan, let's just do the example. I am not getting a question clearly. So I think after that, it should be clear to you. Okay. So just to repeat this. So if the eigenvalues are repeating, then less than n independent eigenvectors are possible. I mean, they may not have, all eigenvectors may be independent or may be dependent. Okay. So let's do the example. Suppose this is a matrix A, which is 3, 0, 1, 3. So let me just find out A minus lambda I, and let's just find out the eigenvalues here. This is 3 minus lambda, 1, 0, 3 minus lambda, right? If you find the determinant, then it will be 3 minus lambda into 3 minus lambda, right? Let me find the determinant along with this column. Okay, you can find along with this row, but that's okay. Like, let me find along with this column, or even if you find along with this the first row, then also this is same, I think, right? Yeah, this is 0. So can you tell me what is the value of lambda? Value of lambda is 3, right? Value of lambda is 3. So since 3 is repeating 2 times, like people write it 3, 3. Otherwise, it is just 3, right? I mean, this is lambda minus 3 whole square, which is 0. It is just 3, but 3 is repeating 2 times. So I am just writing 3, 3. Okay. Now, let's just find out the eigenvectors corresponding to this eigenvalue. How to find out? You just put it in Ax equal to lambda x, right? So in this equation, you just put it. Now, do you know how to solve this Ax equal to 0? How to solve this Ax equal to 0? Set of linear homogeneous equations, you know, right? So how to solve this? Like we convert this into echelon form, if you remember, and then we find out what are the free variables, what are the pivot variables, then we assign values to the free variables, like that, right? And then we find out the values of the x. Do you remember the whole procedure that we did? So we will convert that into like Euclidean form, like that, right? So this is just Ax equal to 0. This is just Ax equal to 0, where lambda will be given to you. So lambda is 3. So if you remember, then just apply that that method that we have already seen. So this is just set of homogeneous equations. Okay. And we know how to solve this. Okay, we know how to solve this. And how to solve this means how to find the value of x. Now a is given, right? A is given to you already in the question. Lambda is also given, which means like lambda we have just found out. Lambda is also given. So this is just a matrix, which is can you just do it? This is 0, 1, 0, 0, right? and into x. You can write it xy or anything equal to 0. So can you solve this? Let me just do it. 0 1 0 0 0 1 0 0. So I'm going with the traditional way of solving, like the way we have done earlier. Okay. So how to solve this? I think we convert this into augmented form, right? And then we convert this into echelon form. So this is not the pivot, and the first pivot is itself at this row, and this is already in the echelon form. So that's okay. Now tell me what are the free variables? This is the variable corresponding to x. This is the variable corresponding to y. Now tell me what are the free variables? X, right? X. So x is a free variable. Now you can do what? You can just this is 0 equal to 0. This is y equal to 0. Yeah, y equal to 0. And x is a free variable. You can take it x equal to k. So what is xy? K0, right? K0. Okay. Now you got k. Let me just write it in this way, like the way we used to write. So k 1 into 0. Is this okay to everyone? How we are finding this x from this a minus lambda equal to 0? Sorry, a minus lambda into x equal to 0. Let me know if there is any doubt. Like this is the same way we have been doing to find the ax equal to 0. Okay, we will just convert this matrix into echelon form. Then we will just find out the free variables. We will assign the free variables. We will use those free variables to find the pivot variable values, and then finally we find the value of x. So I hope that is okay. Now this is corresponding to, this is what we have got corresponding to lambda equal to 3, right? Lambda equal to 3. Now tell me how many independent vectors are there. So if you remember, like we have seen these kind of formulations also, right? I mean, this could be anything. This plus k2 into something like that, right? So these kind of formulations also we have seen. Something like this we have also seen. So at that time, like I have said, there are two linearly independent vectors which are forming the solution x, right? Which are forming the solution x. Okay. So we will get to that. But for now, just tell me how many linearly independent vectors are there. How many linearly independent vectors are there? Only one, right? For lambda equal to 1, for lambda equal to 1, for lambda equal to 1, sorry, lambda equal to 3, you are getting 1 0, right? I mean k1 0. So basically, let me just write, if this is x, if this is x, so you can just say for lambda equal to 1, you are getting x as answer, 2x as answer, 3x as answer, basically like kx as answer, right? So if x is eigenvector, then kx is also eigenvector. Basically, this is the set of all eigenvectors corresponding to lambda equal to 3. Is this okay to everyone? So corresponding to lambda equal to 3, you have these infinitely set of eigenvectors, right? This is infinite set of eigenvectors. You always have infinite set of eigenvectors. You can't have only one eigenvector, because if x is eigenvector, then kx is eigenvector, right? So you can't have only one eigenvector. You always have infinite eigenvectors corresponding to one lambda. Okay. Now tell me, is this okay to everyone? Now, if this is okay, now tell me, are there, like corresponding to one lambda, are there multiple like independent eigenvector, or only one eigenvector that could be independent? Like I mean, can you have multiple vectors which are independent, linearly independent? You can't have, right? There is only one vector, one linearly independent vector, right? For lambda equal to 3, we have just one linearly independent eigenvector, right? Okay. Now hypothetically, like I'm saying you, suppose for lambda equal to 3, I solve this a minus lambda I. So I have the example in the next slide, but like for now I'm just saying you equal to 0. Suppose if I solve this, like I solve this, and then I got lambda equal to, suppose something like this. This is s, okay? Or let me just write k1. Or I hope that is fine. This is s, okay? Not 5. This is s. This is t. This is maybe s plus t. Suppose something like this. Like let's suppose there are three free variables. Sorry, 2 free variables I got, and finally I got this kind of equation. Now tell me, What is the lambda? Like just write it in the right nicer form. Can you write it? Do you remember how to write it? Do you remember the hack that we used? Can anyone tell me? This should be s equal to 0 and t equal to 1. This should be t equal to 0 and s equal to 1, right? So s equal to 0, t equal to 1, 1, t equal to 0, s equal to 1, right? Yeah. So these are the two vectors you got, right? So corresponding to lambda equal to 3, you got this as an eigenvector. Now this is an eigenvector. Now corresponding to lambda equal to 3, you got one eigenvector as like s and t are free variables, right? So you can say one eigenvector is this, another eigenvector is 1 0 0, sorry 1 0 1, another eigenvector maybe the combination of this, maybe just put s and t both are 1. So maybe this. So you can take s and t anything, right? You can take s and t. So here s and t are free variables, right? S and t are free. So you can take it anything, and everything will corresponding to the one of the solution. So if you take s equal to 1, like if you take s equal to 1, t equal to 0, s equal to 0, t equal to 1, anything you can take, and everything is solution. So this is also valid solution. This is also valid eigenvector. You take s equal to 1, t equal to 1. This is also valid eigenvector, right? This is also valid eigenvector. So you can take anything. You will be having valid eigenvectors. Everything, like whatever value of s and t you will take, you will be having valid eigenvectors. Is this okay to everyone? Like what I'm saying? See, you put the lambda equal to 3, like you got some value of lambda, and that happens to be having two free variables. No big deal, right? You can have two free variables. There is no problem here. Like in this case, it was a simpler case. So I was just having one free variable, that was just x, but I may have two free variables also. In that case, I may have got this lambda equal to something like this, maybe two free variables. Then I may get these, like these as the eigenvectors. Like you can put s and t anything, you will be getting eigenvectors, right? S and t reverse written in the solution. S equal to, okay, yes, that's reverse written anyway. Okay, let me just write it t here or s here. Now is this okay? S equal to 0, t equal to 0, s equal to 1. Yeah, it should be okay. Okay, so now what I'm saying that like you can take s and value anything, you will be having many eigenvectors, right? Similarly here also you can take value of k anything, you will be having many eigenvectors, right? K equal to 0 is like, oh sorry, k equal to 0 is not eigenvector. Like I mean, that's by definition it is not eigenvector, as I told you. Like 0 vector is not eigenvector, but yeah, apart from 0 you can take any value, right? This is eigenvector. Similarly, you can take any value of s and t. Both cannot be 0 for the eigenvector. That is a solution, but that's not eigenvector anyway. So you can take any value of s and t, and that will lead to one of the solution. And these are the eigenvectors. But tell me how many independent you have here. Okay, here how many independent you have? Only one, right? Only one independent. But here how many independent you have? Two independent. Two independent. No, here you have two, right? Yeah, here you have two. This and this. So you may be getting infinitely many eigenvectors. That's okay, but you have only two independent eigenvectors which are linearly independent, like two vectors which are linearly independent. So that's what I'm saying. Corresponding to only lambda equal to 3, you may get only one linearly independent eigenvector, right? You may get two linearly independent eigenvectors corresponding to only lambda equal to 3. That's what I'm saying. So corresponding to only one lambda, you may get multiple eigenvectors also, multiple linearly independent eigenvectors also. Okay. Let me know if there is any doubt here. I mean, you can get, that's what I'm saying. So I hope like this is at least clear. Let me move to one more example. Okay. I think from that, yeah. So let's suppose this is a given matrix, and you want to find out the eigen values and eigenvectors. So just to simplify things, I have written the eigenvalues. Like I'm not going to calculate it, but these are the eigenvalues which we are getting. Okay. Let's just find out the eigenvectors directly. So how to find out the eigenvectors? A minus lambda should be, sorry, a minus lambda into x should be 0. So this is how we want to find, we will find the eigenvectors. So let me just do it. A is, let's suppose I want to find out for first lambda equal to 6. So A is 5 minus 6 minus 1 0 minus 1 5 minus 6 0 1 by 3 minus 1 by 3 4 minus 6. into x, right? Into x equal to 0. So anyway, let me just write it in the way that we used to write 0 0 0 equal like that, right? Is this okay to everyone? Okay, so I hope that is fine, right? Like I have just written this in that way, so I hope that is fine. Now let me just find the solution. So how to find the solutions? We to find the solutions, we just convert this into echelon form, right? So let's just do it. This is let me just write it simply. -1, this is -1, this is 0, this is -1, this is again -1, this is 0. Oh, these two are same. This is 1 by 3, this is -1 by 3, this is -2, this is 0 0 0. Is this okay to everyone? Now I'm getting, let me just get rid of this 3 1 by 3, because since this is like linear set of equations, so I can just use this, right? I can just use this. In the determinant I can't use this, but I can just multiply 3 in this last row. That's okay, right? So I can multiply 3 in the last row to get rid of this 3 in the numerator. So if I do it, then it will be just 1, it will be just 1, it will be -1, it will be 1. You people are getting, right? I'm multiplying 3 in the last row because I can do it. It's just a set of equations. This is -1, this is -6. Okay. So let's just quickly do it. Let's convert this into echelon form. This is -1. You can just apply anything. You can just R1, R2 gives R2 minus R1, something like this. R3 gives R3 plus R1. Okay. So if you subtract R2 minus R1, you will be getting, this is -1, -1, 0, 0. If you subtract this from this, you will be getting 0, 0, 0, 0, obviously. And if you just add this 0, 0, -6, right? And then you can swap these two rows. This is one pivot. And then if you swap these two rows, this is -6 and this will be 0, right? This is -6, then this will be 0. Then this is another pivot. So what is the free variable here? Is this okay, or have I done some mistake? Okay, this is -2. Okay, 1 second. This is -2, is it? Okay, so this is the pivot, right? Not -6. Anyway, so -6 is not pivot, -2 is pivot. Okay. So -2 is pivot, and what is the free variable here? Free variable is x, y, z. If I'm calling it x, y, z, this z is free variable. So z equal to k, and then you can just do it. Let me just quickly do it. So z equal to k, and then what you will be getting? You will be getting -2y minus 6z equal to 0. Okay. -2y minus 6z equal to 0. Z is k, and one more equation you are getting, which is -x minus y equal to 0. -x minus y equal to 0. So from this you are getting what? You can just divide by 2. This is -2, or maybe this is y equal to 6z, then minus 3z minus 3k, and x equal to x and y are having different signs, I think. So this is 3k, right? So yeah, so you are having x, y, z like this. This is 3k minus 3k, this is k, and then this is k, you can take common, 3 minus 3, right? Now tell me, corresponding to lambda equal to 6, how many independent eigenvectors you got? How many independent eigenvectors you got corresponding to lambda equal to 6? So only one linearly independent eigenvector, right? So let me just show you corresponding to lambda equal to 4. Okay, so this is the matrix that we are getting, and let's just solve this matrix. So I'm not going to so basically, if you just put lambda equal to 4, you will be getting this. Let's not worry about these two vectors or something. We will drive what we are going to get. So till now I'm just using this fact that you are going to get this matrix, which is 1 minus 1 0. Okay, so a minus lambda I, this matrix is basically this 1 minus 1 0, and minus 1 1 0, minus 1 1 0. So my 1 by 3 minus 1 by 3. Okay. So let me just also append zeros. This is corresponding to lambda equal to 4. Okay, corresponding to lambda equal to 4, we are getting this. Now let me quickly solve it. Let me just multiply by the 3 again, because let me just get rid of this 3. Okay, this will be minus 1, and I think you can just add, or maybe R2 gives R2 plus R1, R3 gives R3 minus R1. Can you do it quickly? So it will be 1 minus 1 0. This is 0. This is 0 0 0 0. This is R3 minus R1, right? So this is 0, and then this will be again 0. This is again 0. Okay, this is again 0. So okay, now tell me, this is the pivot variable. What are the free variables? Suppose this is x, this is y, this is z. What are the free variables? Y and z, right? Free are y and z. Now here, yeah, we have got two free variables, right? So let me take y equal to s and z equal to t. Okay, and then you have x minus y equal to 0 from this, right? So x equal to, you got s, right? X equal to s you got. So x, y, z is, I hope that calculation is okay to everyone. So x equal to s you got, y equal to s you got, t. So SST. Okay, so you finally got x, y, z as SST, which is nothing but, like, you can write s equal to 1, s equal to 1 1, t equal to 0, plus t equal to 1 1, and s equal to 0, right? So 1 1 0 0 0 1. Yes. Now this is corresponding to lambda equal to 4. Lambda equal to 4. This corresponds to lambda equal to 4. Now tell me how many number of linearly independent eigen vectors for lambda equal to 4. So just corresponding to one lambda, you have two linearly independent, right? Two linearly independent eigenvectors, right? Can you have three? Three linearly independent? Like, this is the complete set of solution. Whatever you do, you will get at most two. Like, you can put, like, this is a linear combination of two linearly independent. This vector and this vector is linearly independent. So linear combination, this two linearly independent cannot produce three. This can produce two only, at most two, right? If you take all the combinations, then two. So corresponding to lambda equal to 4, you are getting two linearly independent eigenvectors. But corresponding to lambda equal to 6, you are getting only one linearly independent eigenvector. So that's what I was saying, that if you have lambda, one second, yeah, that's what I was saying here. If you have lambda 1 equal to lambda 2, which means, like, actually, like, this is not lambda 1, lambda 2, both are same actually. So if you have same lambda, so corresponding to the same lambda, you may or may not have linearly independent eigenvectors, right? So see here you have only one linearly independent eigenvector, or even though your eigenvalues are repeating, your eigenvalue is repeating two times, even though you are only having one linearly independent eigenvector. But here, if you are having repeating eigenvalues, then you have two linearly independent eigenvectors, right? So repeating eigenvalues may or may not give you linearly independent eigenvectors. That's what I was saying. Eigenvectors are always taken from independent vectors in solution of Ax equal to 0, not from Ax. No, eigenvectors are not the solution of Ax equal to 0. Eigenvectors are solution of A minus lambda into X equal to 0. Okay. Eigenvectors are not the solution of Ax equal to 0. Eigenvectors are solution of A minus lambda into X equal to 0. So yeah, you can say, so the eigenvectors are always taken from the independent vectors. Independent vectors means what? This every vector is eigenvector here. Like, whatever you take the value of S and T, like, it should not be 0, like both should not be 0 at the same time, but whatever value you take from this, right, S and T, every vector is eigenvector. This is the complete set of eigenvectors. You can take, these are the infinite set of eigenvectors. You can take any eigenvector from there. That you can take any vector from this space, that vector is eigenvector. Yes. Every eigenvector is generated from with the help of these two vectors. Yes. I mean in this example. Okay. So now let's come to one last theorem. What's the time now? It's 11. Okay. Should we do it tomorrow? Can a matrix have only one eigenvector? No, one eigenvector is not possible. If x is eigenvector, then kx is also eigenvector, right? Okay. So let me just read out this statement and then we will do it tomorrow. So the statement says that, okay, actually I think it will just take, I don't know, half an hour more maybe. ठीक है, कल कर लेते हैं. एक्चुअली ज्यादा बचा भी नहीं है, बट ठीक है, चलो कल कर लेते हैं. Okay, we will do it tomorrow. Let me just read this statement and then we will do it tomorrow. Okay, let's just do it tomorrow only. Basically, the statement was like this: that if we have any matrix, like do we have any condition after which we are always sure that we have independent eigenvectors, and the condition is that for the symmetric matrix. For the symmetric matrix, it doesn't matter whether the values are repeating. I mean, whether you have lambda minus 3 square into lambda minus 2 or anything, like eigenvalues are repeating or not repeating, or whatever. Like it doesn't matter. For the symmetric matrix, you always have independent eigenvectors. That's very important for the symmetric matrix, and that's actually very useful in the machine learning also, like symmetric matrices. Okay, let's do it tomorrow. So I'm taking the doubts now. If you do not have any doubt, then you may leave. Yeah, Digvijay, can you speak?
Hello, sir. Am I audible?
Hello.
Hello. Am I audible, sir?
Okay, one second.
Hello.
Yeah, Digvijay, now I should be able to hear you. Can you speak?
Hello, sir. Am I audible now?
You're speaking.
Hello. So, sir, when we have an n into n matrix, and for that we have n eigenvalues, right? So then if two eigenvectors corresponding to different eigenvalues, they must be linearly independent. Am I correct here?
Two eigenvectors corresponding to different eigenvalues, yes, they will be linearly independent. Yes.
Linearly independent. And
Yes.
in the same case, if two eigenvectors are corresponding to same eigenvalue, then they need not to be linearly dependent. Is that correct?
Yes.
For this, okay. And now for when number of eigenvalues are less than n, then for then are this, like, for unique eigenvalues, is the scenario exactly same as when you had a
Number eigenvalues are less than n. Yes, if the eigenvalues are less than n,
yes.
so suppose let's suppose like this is 4 into 4 matrix and I have lambda 1, lambda 2, lambda 3. So basically, now I may or may not have linearly independent eigenvectors. Now basically corresponding to lambda 1, let's suppose lambda 1 is repeating 2 times, okay? Lambda 2 is only 1 time and lambda 3 is only 1 time because the polynomial has to be of degree 4. So it will be lambda 1 minus, lambda minus lambda 1 whole square into lambda minus lambda 2 into lambda minus lambda 3. So here corresponding to it, it is not necessary that corresponding to lambda 1 you will be having two independent linearly independent. You may have only one, as we have seen one example of this 3 0 0 1 3 some matrix, some 2 by 2 matrix was there, right? So here corresponding to lambda equal to 3, we just had only one linearly independent vector.
Okay, so since lambda 1 is repeating 2 times, so that's why, like, I'm still a bit confused. Like, if
Actually, see,
one vector
for every matrix you do not have independent eigenvectors. Like otherwise every matrix will be a nice matrix. So symmetric matrices are very useful because we always have independent eigenvectors. But for every matrix, we do not have independent eigenvectors. Even for some matrices, like we do not have any, even single eigenvector.
Okay. Like here, lambda 2 is not same as lambda 1. So if eigenvectors corresponds to lambda 2, then it needs to be then a eigenvector corresponding to lambda 1 and the eigenvector corresponding to lambda 2, they must be different, right? But they
Yes, yes,
must be linearly independent.
yes, yes. They
That
have
still
to be.
holds here.
Yes.
But since lambda 1 is repeating two times, that's why we say that one, like it is repeating two times, so two, so
Yes, yes.
like
Two
two
linearly
vectors,
independent may
one
be.
from,
Yes.
like one can be from the one can be from one copy of lambda 1 and other can be from one copy of lambda 1, and they can be dependent.
Yeah, so if
Am I
lambda one
interpreting it
like
correctly?
is actually this is only one lambda one. Like there are not two, but yeah, we can say like repeating or all. So if in that case the linearly dependent need not to be necessary linear independent. So you may have only if in the solution in the ax a minus lambda into x equal to 0. If you solve this, then the number it depends on number of free variables. If you have only one free variable, then there is only one linearly dependent. If you have only one free variable, something like this. If you have only one free variable, then only one linearly dependent. If you have two free variables, you have two linearly dependent.
Okay, sir, we had that diagram where less than, we had n equal to n and less than n around page 9, slide 90, I think.
Okay.
Can you go to that
Yes.
once? So, eigenvectors. No, like
Yeah. This one.
we
Huh?
were, yes, yes.
Hmm.
So, repeating values less than in independent eigenvectors may have.
So basically, if they are repeating values,
Okay,
then
okay,
you
sir.
may have
Okay.
less than n, or you have equal to n, or you may have equal to n.
Yeah, okay, okay. Got it now, sir.
Okay.
Thank, thank
Thank
you.
you. Okay. Thank you, everyone. So let's meet tomorrow, and then we will maybe tomorrow or day after tomorrow. Like I will tell you, and then we will complete this. Okay. Thank you. Yeah. Rajan, one second. Rajan, are you able to speak? Hello. One second. Yeah,
Hello.
Rajan. Yes, yes.
Yes, sir. For let's say two free variable case, k1 into something plus k2 into something. Okay.
Mm-hmm.
So then in this case, how many linearly independent eigenvectors are there?
Hello. Yes, Rajan. So one second, I lost you. So if you have, hello, can you hear me, Rajan?
Yes, yes, I can hear you.
So if you have two free variables, then how many linearly independent eigenvectors?
Yes.
So two linearly independent eigenvectors. You have two free variables.
Uh, that each means part of one part of solution is a eigenvector, right? Means k1 into something is one eigenvector and k2 into something is another eigenvector, right?
Yes, one second. Let me just write it here. So if you have two k1 into something plus k2 into something, so whatever value of k1 and k2 you put, you do not put both to be zeros, because zero is not an eigenvector. So whatever value of k1 and k2 you put, everything is eigenvector. From this space you can take anything apart from the zero vector. Everything is eigenvector. Any linear combination of this, you can put k1 equal to 0, you can put k2 equal to 1, you can put k1 equal to 1, you can put k2 equal to 1, anything, any value of k1 apart from this. Both I mean both cannot be zero at the same time. I mean zero vector is not the eigenvector. Apart from that, you can take any value of k1 and k2.
No, that I got.
Okay.
This complete summation is one eigenvector.
Yes,
That
yes.
you are.
I mean, this is not the vector. Like this is not even a vector. Like this is the parametric form. So specific values are vectors.
Yes, specific value.
Yes. So
So here
basically,
two
yeah.
linearly independent vectors are there. That I got means that part one k1 1 0 0 and k2
Yes.
0 1 0 something. That two linearly independent vectors, right? And this complete thing is a one eigenvector, right?
No, this complete thing is not even a vector. Basically, this complete thing is just a parametric form. I mean, this is not a vector. You can, if you put the value of k1 and k2, then you get the vector.
Okay.
So basically, like, if I say that ax equal to 0 has a solution of x equal to k into something, then basically this is just a parametric form. But we take the specific values. We put the value of k, and then we say that this is a solution. And there are infinitely many solutions. So this is just a compact way of representing it. Like any vector from this space is an eigenvector. This is called eigenspace basically. Any vector from this space is eigenvector.
For this parametric form, can you take one specific example? Means for k1 into write something 1 0 and 0 1 k.
Yeah, let me write like this 0 1 1 maybe.
Yes.
So if you put, let's suppose k1 equal to 1 and k2 equal to 1, then one of the vector you will be getting is this 1 1 and 2. This is eigenvector.
Yes, this is one eigenvector, right?
Yes.
And for another value, we have another eigenvector.
Yes. So if you put k1 equal to 0, k2 equal to 1, and k2 equal to k1 equal to 1, k2 equal to 0, then you will be getting one eigenvector from here, you will be getting one eigenvector from here, and both of those eigenvectors, basically you will be getting this, right? You will be getting this and you will be getting this. And both of those eigenvectors like are linearly independent. That's why you can have at most two linear, you can have two linearly independent eigenvectors for the corresponding lambda.
No, likewise, if I take k1 into k2 many values, then we will have many linearly independent vectors.
No. In R3, you can have at most three, first of all. And if you start with two linearly independent vectors, you can't have more than two. Like whatever vector you are getting, that is ultimately the summation of these two, right? So that cannot be linearly independent of these two vectors individually, this vector and this vector. Whatever vector you are getting, this is a linear combination of these two vectors. That cannot be
Yes,
linearly independent of these two vectors.
yes. Got it.
Yes. So Digvijay, greater than n eigenvectors are not possible because in fact in Rn, at most you can have n linearly independent vectors, right? So at most you can have n linearly independent eigenvectors or any vectors. Yes. Okay. Thank you everyone. Let's finish this in next class. Okay. Bye bye. Good night. Hi everyone. Good morning. Can you hear me? Hi Ashish, how are you? I'm good. Let me share the Zoom link. Okay, so let's start. One second. Yeah. So today we will be talking about few more topics in eigenvalues and eigenvectors, and I have listed down the topics. So let's go over them one by one. So we have already proved that if two eigenvalues are not equal, let's suppose lambda 1 and lambda 2, if they are not equal, then corresponding eigenvectors which are e1 and e2, suppose, then they are what? Linearly independent, right? Linearly independent. So we have already proved this, right? Now, this, like how to prove, this is not important, like how to go about this proof. What is important is this result, that if lambda 1 and lambda 2 are not equal, then corresponding eigenvectors are linearly independent. This is very important. Like you should remember this result, that if lambda 1 and lambda 2 are two eigenvalues which are distinct, then their corresponding eigenvectors has to be linearly independent. Like how to prove it, it is also easy, but like you do not need to remember the proof. You need to remember this result, this result, right? So we have proved it in such a way, like we started with C1 E1 plus C2 E2 equal to 0. Then like if we want to prove that the only solution for the C1 C1 E1 plus C2 E2 equal to 0 is that all CIs are 0. Then we multiplied this with A, then we multiplied this with lambda 1, and then we came up with this something like C1A E1 plus C2A E2 equal to 0. And if we multiply with the lambda 1, then we came up with something like C1 lambda 1 E1 plus C2 lambda 1 E2 equal to 0. And from here we can say that the C1A E1 is nothing but C1 lambda 1 E1 plus C2 lambda 2 E2 equal to 0. And this is equation number 1, this is equation number 2, and from these two equations I can say, if I subtract these two equations, then I will be getting, C2 E2 into lambda 1 minus lambda 2 equal to 0. And since lambda 1 minus lambda 2, like this lambda 1 is not equal to lambda 2, so I can say that this is non-zero, and E2 is eigenvector, so it has to be non-zero. That's why I can say that from here I can say that C2 equal to 0 is the only possible solution, right? Only possible solution. Since C2 equal to 0 is only possible solution from here, and then if I substitute the C2 equal to 0 to this equation, like C1 E1 plus C2 equal to 0, so I will be getting C1 E1 plus 0 equal to 0. If I substitute C2 equal to 0 in this equation, then I can say that C1 E1 equal to also 0. And since E1 is not 0, then it will, like, only possibility is that C1 equal to 0, right? If E1 is not 0. So anyway, like we can prove that C1 and C2 both has to be 0 to satisfy this. But again, proof is not important. What is important is the result, that if two eigenvalues are not equal, then their corresponding eigenvectors has to be linearly independent. Okay, just remember this result. Now there are like two more properties about the real symmetric matrix that you are going to see, and there are two more theorems, basically one or two more theorems we will see here. But before that, let me go over a few examples. Okay, so we have already done this example yesterday, like in the last class, which were like we started, like this was the matrix given, and we wanted to find out the eigenvalues and eigenvectors. So it's just very easy. Like you can just, if this is A, you can just find out A minus lambda I, right? Determinant of A minus lambda I, which is 3 minus lambda, like that you can find out. And from here you are getting lambda equal to 3, 3, like you are getting repeated eigenvalues. Then you put lambda equal to 3 here, and to find out the value of eigenvector, basically A minus lambda I into x equal to 0. This is how you find the eigenvector. And you know how to solve this system of linear homogeneous equations, right? So you just need to put the value of lambda, which is this, and now you need to solve this. So what is the free variable here? Like suppose this is corresponding to x, this is corresponding to y, then what is the free variable here? X is a free variable and y is a pivot variable, right? Y is a pivot variable. So if x is a free variable, then you can assign any value to x, and then you can solve for y. So it will be like, from this first equation you can say that y equal to 0. So this is the solution that you get, and like you can just put that into a vector form. So it will be like this is the solution that you're getting. Now you notice one thing, that lambda is repeating 2 times, and here I'm getting here I'm getting only one linear independent eigenvector corresponding to lambda, right? Which is this 1, 1, 0. Now basically corresponding to one eigenvalue, let's suppose lambda 1 or lambda 2, anything corresponding to one eigenvalue, we can, if x is eigenvector, then we know that if x is eigenvector corresponding to lambda 1, then we know that 2x is also eigenvector, 3x is also eigenvector, like that we know, right? So these are linearly dependent, that's okay, but corresponding to one eigenvalue also, like we can have multiple linearly independent eigenvectors also. Okay, so maybe like x is one vector, maybe y is one vector corresponding to lambda 1 only. Okay, so we can have multiple linearly independent eigenvectors also. So if x is one vector, then obviously 2x is eigenvector, 3x is eigenvector, that I agree. But if x is one vector, then there could be some linearly independent eigenvector also corresponding to lambda 1 only. Okay, so if let's suppose this is y, then obviously 2y is also eigenvector, that is okay. But what I'm saying that there could be multiple linearly independent eigenvectors corresponding to only lambda 1. Okay, so we will see this in more detail today, and that is called multiplicity. So multiplicity, that is called multiplicity. So we will see that in more detail today. Okay, so anyway, like we have also seen one more example yesterday, that for this matrix, if we solve for eigenvalues, then we are getting this lambda equal to 644. These are the eigenvalues that we are getting. So let's suppose this is lambda 1, and let's suppose these are lambda 2. Okay, this is lambda 2, and yeah, lambda 2 is repeating 2 times, but that's okay. So corresponding to lambda 1, I'm getting, like, you can solve this a minus lambda 1 I into x equal to 0, right? So this is system of homogeneous equations. So you can solve this, and corresponding to this lambda 1, I'm getting this as an answer. Okay, because there is only one free variable, like we have solved this in the last class. Corresponding to lambda 2, we got two free variables, like I think y and z, or x and y, like y and z, I think we have got two free variables, and then we have got two linearly independent eigenvectors corresponding to this lambda 2, right? So corresponding to lambda 2, corresponding to this 4, lambda 2 equal to 4, right? We have got two linearly independent eigenvectors. I mean, let me go into the more detail. See, lambda 2 equal to 4, so we got the solution like this: 110 and 001, right? 110 and 001. So we got this solution corresponding to lambda equal to 4. This is like s, and this is t. Okay, now you can put any value of s and t, like apart from the 0 vector. You can take any vector from this linear combination. So you can put any value of s and t, and every vector will be the eigenvector corresponding to lambda 2 equal to 2, lambda 2 equal to 4, right? So let me put, if you put like s1 equal to 1 and t equal to s equal to 1, t equal to 0, then what you will be getting? You will be getting 110, right? This is eigenvector. This is eigenvector, right? Similarly, you can this, I got this by putting this value. Okay, similarly you can put maybe t equal to 1 and s equal to 0, so you will be getting this. So this is also eigenvector, that you got t equal to 1, s equal to 0. You can put any other value also, like you can put s equal to 1, t equal to 1, right? So this will be again eigenvector. You can put s equal to 1, t equal to 1, then it will be 1 1 1, right? This is again eigenvector. You can put s equal to 2, t equal to 2, s equal to 2, t equal to 2, anything you can put. So this will be again one new eigenvector. So if you put s equal to 2, t equal to 2, it will be 2 2 2, right? So you can put anything. You can put the value of s and t, anything apart from both to be 0, because eigenvectors are not 0 vectors. So that is why you can't put s equal to 0, t equal to 0. Apart from that, you can put anything, and you will be getting eigenvectors. Now tell me, out of all eigenvectors, how many eigenvectors you will be having as linearly independent? Since these two eigenvectors are linearly independent, that you all agree. So in the solution of x equal to 0, like if x equal to whatever I'm getting, something plus something, right, as t, so these two has to be linearly independent, right? You remember from solution of x equal to 0, if I'm getting this kind of solution, then these two vectors has to be linearly independent at least. So this vector and this vector is linearly independent. Why? Because as you see here, that this is like, see, at one place t is 0, at another place t is 1, right? So this is 0 and this is 1. So you can't produce one from another. Just by looking at these two entries, you can say that you can't produce one from another. So these two vectors are linearly independent. At least these two vectors we agree linearly independent, right? These two vectors. So we have seen this in solution of x equal to 0. So these two vectors are linearly independent. Now, if you put s equal to 1, t equal to 0, you will be getting one of them. You put s equal to 0, t equal to 1, you will be getting one of them, right? So these two vectors you will be definitely getting as eigenvectors, right? So you can pick this by choosing s and not choosing t. You can pick this by choosing t, not choosing s, right? So these two vectors will definitely be eigenvector. You can put s equal to 1, t equal to 1 also. You can put various combination and everything will be eigenvector corresponding to lambda 2 equal to 4, right? So how many eigenvectors will be independent? Since you are starting with two linearly independent eigenvectors, you can't get more than two. That is for sure. Like you are starting, see, you can't get more than two linearly independent eigenvectors if you are starting with just two linearly independent vectors, right? Why? Because suppose you are getting more than two, then what will happen? Suppose you are starting with two vectors, two linearly independent vectors. Okay, this vector, let's suppose v1, this vector is v2, and you are starting with these two vectors, and you are getting let's suppose you are getting three linearly independent vectors. Is it possible? Like you are starting with two linearly independent vectors, and by their linear combination, can you get three linearly independent vectors? Tell me, is this possible or not? This is not possible, right? Why? Because suppose if this is possible, then you can, let's suppose this is R3. Okay, let's suppose this is R3. Then basically you just need two linearly independent vector, and then you can fill the whole space, right? Like from these two vectors you can get the three vectors, and from these three vectors you can fill R3, right? You can fill R3. So basically, anyway, like these arguments doesn't make sense. Like you can't get more than two linearly dependent eigenvectors or vectors. If you just start with two linearly independent eigenvectors or vectors, you can't get more than two linearly independent vectors, right? So there are two linearly independent vectors, and these are the eigenvectors. And at most, like I mean, you can get only two linearly independent eigenvectors. You can't get more than two. So I hope that is okay with everyone. Okay, so for lambda 2 equal to 4, I am getting two linearly independent vectors. But for lambda 1 equal to 6, I am getting only one linearly independent vector. Now, one thing is to note here is that lambda 2 is repeating how many times? Two times. And how many vectors I am getting? Two linearly independent eigenvectors. But it is not always necessary. Like in the earlier case, it is also repeating two times, but I am getting just one linearly independent eigenvector, right? So it does not mean if it is repeating multiple times, then I will get that many linearly independent eigenvectors. Okay, see here, it is repeating two times, but I'm getting only just one linearly independent eigenvector. Here I'm repeating two times, and I'm getting two linearly independent eigenvectors. That's okay, but it is not necessary. In general, if my eigenvalue lambda is repeating, let's suppose m times. Okay, that I will talk about it a little later, but I'm just telling you like bit ahead. So suppose if lambda is repeating m times. Okay, what does this mean? This means that lambda, let's suppose lambda 1 is repeating m times. So this means that like in the characteristics polynomial equation, you are having some factor like this, right? Maybe lambda minus lambda 2, something like this. Maybe lambda minus lambda 3, something like this, equal to 0. So you are repeating this lambda 1 m times. Is this okay to everyone? What does this repeating m times means? Repeating m times means you have in the characteristics polynomial equation, you are having something like this. Then you are saying that lambda 1 is repeating m times, right? Now corresponding to this lambda 1, how many linearly independent eigenvectors I have? Linearly independent eigenvectors. I may have only one linearly independent eigenvector. I may have two, I may have three, I may have four, I may have at most m, that I will talk about little later. So basically, if this is repeating m times, then I can have at most m linearly independent eigenvectors corresponding to lambda 1. Okay. So if this is repeating two times, suppose here it is repeating two times, so I can have at most two linearly independent eigenvectors. Okay, if it is repeating two times, so I can have at most two linearly independent eigenvectors. If it is repeating two times, I can have at most two linearly independent eigenvectors. It doesn't mean that always two. Okay, here it is one. You're getting. So if it is repeating two times, it means that I can have at most 2 linearly independent eigenvectors. Okay, so here it is repeating 2 times, I can have at most 2 linearly independent eigenvectors. If it is repeating m times, so I can have at most m linearly independent eigenvectors corresponding to lambda 1. Okay, so this is called multiplicity. So we will talk about it later, but I'm just telling you a bit ahead that if lambda 1 is repeating m times or 2 times or 3 times, if it is repeating 3 times, then you can have at most 3 linearly independent eigenvectors. You can't have more than 3 linearly independent eigenvectors corresponding to lambda 1. Yes, you can definitely have less than 3. Okay. Yes, obviously, like one linearly independent eigenvector that will always be there. Okay, so let's take one more example. Let's suppose if this matrix is given to you and I want to find out the eigenvalues and eigenvectors. So let me just go to the next page. So 0, 1, what was that matrix? -1 and 0. So let's just do it. Let's just find out the eigenvalues and eigenvectors for this. So how to find out the eigenvalues first? A minus lambda I, determinant of A minus lambda I equal to 0, right? This is how we find out the eigenvalues. So let me just find out the determinant of this. This is -1, -1, minus lambda, right? Sorry, this is determinant. So 1 second. Okay, so this should be 0. Now from here you can say that lambda square, okay, lambda square minus -1, which is +1, equal to 0, right? So you can say that lambda equal to plus minus iota, right? It will be imaginary. So eigenvalues and eigenvectors always need not to be real. So it may be the imaginary eigenvalues or eigenvectors. Okay, is this okay to everyone? Like how we are solving this? So I just find out the determinant, and lambda square +1 happens to be 0, and from here I can say that lambda square is -1. From here I can say that lambda is -1 plus -1, which is plus minus iota. Okay, so everyone understand that x square equal to 4 means what? Like if I solve x square equal to 4, then x equal to square root of 4 plus minus, right? Which means plus minus 2, right? So it does not mean that like I told earlier also, it does not mean that square root of 4 is not plus minus 2, right? So you understand this, right? So square root of 4 is always plus 2. Like square root is a function which is deterministic. Like function just give one value, it doesn't give two values. So square root of 4 is always plus 2. It is not plus minus 2. Plus minus is coming because you are taking you are basically taking the square root both sides. So you need to consider both the possibilities. You need to consider both the possibilities. It is plus minus. It is this plus minus is not because the square root. This plus minus is because you are coming from here to here. So that is why you are getting this, right? So, sir, how it is possible that agent lambda is scalar? Here, lambda is scalar. So, scalar doesn't mean the real numbers. So, imaginary numbers are also scalar. So, here lambda is scalar. I'm not saying lambda is vector, but lambda is equal to plus minus iota. Okay. So, now let's just find out the eigenvectors. So, eigenvalue is plus minus iota. Now, there are two eigenvalues. So, basically, lambda 1, let me just find out eigenvectors corresponding to lambda 1, which is iota, and corresponding to lambda 2, which is minus iota. Okay, and what is my matrix? Matrix is 0, 1, -1, 0. Matrix is 0, 1, -1, 0. Okay, yeah. So basically it is skew symmetric matrix, and skew symmetric matrix have the, even though the matrix is real, but skew symmetric matrix have the imaginary eigenvalues, and the symmetric matrix has the real eigenvalues always. So I mean, real symmetric matrix has real eigenvalues, and real skew symmetric matrix has imaginary eigenvalues. But anyway, like this is not important, like to remember that whether it is skew symmetric or not. You can just find out the eigenvalues and we can just solve for it. So can you find out the eigenvector corresponding to lambda equal to iota? How to find out? A minus lambda I into x equal to 0. You just need to solve this system of linear equations. So what is A here? A is this matrix, and lambda 1i, right? Lambda 1i. So you can just solve it. Let me just quickly do it. This is basically minus iota 1 minus 1 minus iota And since I'm solving the system of linear equations, homogeneous equations, so let me just have the augmented matrix. Is this okay to everyone? How I'm getting this? I just want to solve for a minus lambda I into x equal to 0. Okay, I just want to solve for this matrix. Now you can make this this one element as a pivot element and tell me what should we. I think yeah. So you can just tell me R1 R2 gives R2 minus IR1, I think, right? So it should be, if you just apply this, it will be minus I1 0 as it is, and then it will be 0 0. See, I square is minus 1, and if you just multiply with I here and subtract, this will be 0, and if you just multiply I here, I in R1, right? So minus I square is plus 1, right? Minus I square is plus 1, and R2. So should I have, this is, let me do IR2 minus R1. Yeah, this is good. IR2 minus R1. So IR2 minus R1 will be minus R2. Yeah, that should be good. So it is 0. And if you just multiply I with this minus I, it will be I into minus I square, which is 1. And if you subtract this, then it will be 0. This is 0, right? So this is pivot element, and you can see that below this pivot element, everything is 0. And there is only one pivot element. And if this is x, this is y. So can you tell me what is the free variable? Free variable is y, and pivot variable is x. So you can solve for x. Let me just take it k. So you can just say that minus ix plus k or plus y equal to 0. So from here you can get x equal to k upon I, right? K upon I. Okay, x equal to k upon I you got, and you can just say that x y equal to k upon I. Basically, k upon I, you can just multiply I both sides. Like instead of having a complex number at the denominator, I can have ki upon I square, right? I square is minus 1. So you can have minus ki. Is this okay to everyone? See, k upon I is like generally we do it in 11th or 12th class. So instead of having the complex number in the denominator, I just want to have this on the numerator. So I can just say that it is basically ki into I square. Yes, right? So it is ki upon minus 1, which is minus ki. Okay, so k upon I is minus ki. So let me just write it minus ki instead of k upon I, right? We can do it. So this is minus ki, and y is k. So you can take the k common. You got minus I and 1, right? You got this. Similarly, you can solve for lambda 2 equal to minus I. I'm not going to solve it. You can solve it. So basically, like eigenvalues need not to be always real. Okay, this could be the imaginary eigenvalues also. But by the way, like what does this imaginary eigenvalues and imaginary eigenvector mean? So this is a complex eigenvector. This is not a real eigenvector. This is a complex eigenvector. So let me tell you the geometric interpretation, if that makes sense here. So see, the matrix was this 0 1 minus 1 0, right? This was the matrix. Do you remember the geometric interpretation of eigenvalues and eigenvectors? Anyone? So eigenvector, the geometric interpretation is that if x is your eigenvector corresponding to a, then if you multiply a with x, you will not be changing its direction. It will be, direction will be same. It may get stretched, it may get shrunk, but the direction will be same. So it is ax or lambda x, right? It is ax or which is lambda x, right? So this is a geometric interpretation. Now let's see, like let's see if I multiply this with some vector xy, then what I'm going to get. What I'm going to get, it is basically saying x times this vector and y times this vector, it is y minus x, right? Okay, so if I multiply this matrix A with some vector xy, then I'm getting y minus x. Do you notice one thing, that this matrix, if you multiply with this vector, can this matrix have any eigenvector, which means can this vector xy be a scalar multiplication of this y into, see, to be a eigenvector, you need to have a into some vector should be k into the same vector. But what I'm getting here, I'm getting y minus x, right? See, x, y, and y minus x are actually like, can they be parallel? Can they be in the same direction? They can never be in the same direction. Why? They are actually orthogonal. So if you just take the dot product between x, y dot y minus x, so it means like dot product means like, if you remember taking the dot product between u1 u2, so it will be like, let me just write it, u1 v1 plus u2 v2, right? This is the dot product. So if you just take it, that this will be xy minus xy or something, it is 0. So which means like this vector and this vector are actually orthogonal, which means you multiply this matrix with some vector, it is always rotating by 90 degree. This matrix is rotating every vector by 90 degree. This cannot keep any vector in the same direction. You getting? So basically, eigenvectors are what? Eigenvectors are vectors. If you, there exists some vector, if you multiply with the matrix A, that does not change its direction, it keeps the direction same. But my matrix is such that that it actually rotate every vector. It does not keep the direction of any vector same. You multiply any vector xy, it will rotate it with a 90 degree by minus y x, right? It is rotating every vector. It is not keeping any vector direction same. So that is why there is no real eigenvector for this matrix. Because if there is at all any eigenvector, then this matrix should preserve its direction. But it is not preserving any direction. It is rotating every vector by the 90 degree, right? This matrix is rotating every vector by 90 degree. Is this okay to everyone? See, you multiply with any vector, you are getting some vector which is the rotated vector by 90 degree. This is the orthogonal vector. These two vectors are orthogonal, right? These two are perpendicular to each other. So this matrix is rotating every vector by 90 degree. It cannot preserve the direction to any vector. That is why there is no eigenvector for this. That is why there is no eigenvector, no real, basically, no real. You can't interpret this eigenvector in the real coordinate system. No real eigenvector for given matrix. Because this is a rotation matrix, right? So rotation matrix never have the eigenvectors. Is this okay to everyone? Like this is I'm just telling you the geometric interpretation, but for our exam, this is not much important. For our exam, you should be able to find out the eigenvalues and eigenvectors like that. So I think you can do it. You can just subtract like this, and you can just find out the eigenvalues, and based on the eigenvalues, you can find out the eigenvector, right? Is this because eigenvalue is negative as well? No, eigenvalue negative doesn't matter. So because of eigenvalue negative doesn't matter. Imaginary, yes. So eigenvalue is imaginary. That is why, like, yeah, you can say this. So basically, eigenvalue is imaginary, and why eigenvalue is imaginary? Because the eigenvector, there is no eigenvector itself. So everything is in the complex system, like not in the real number, real coordinate system. So anyway, let me move to the next question. So let's just find out the eigenvalues and eigenvector for this matrix. So we are like, let me just do a couple of questions and then we will move to theorems. Okay. So let's just find out the eigenvalues and eigenvector. If you can do it quickly by your own, it will be very, very good. And meanwhile, I'm also doing it. So just find out the a minus lambda equal to 0. Just find out the a minus lambda equal to 0. It will be, I think, 1 minus lambda 0 0 1 1 minus lambda 1 0 0 1 minus lambda, right, equal to 0. Now if you solve this, it will be 1 minus lambda into determinant of this, right? So you are let me just expand along with the first row. So 1 minus lambda into determinant of this, which is just 1 minus lambda whole square, right? 1 minus lambda whole square. So it is equal to 0. It is just lambda equal to 1 1 1, right? 3 times 1 1 1 3 times. Now let's just find out the eigenvectors also. This is the eigenvalue. Let's just quickly find out the eigenvectors also. So how to find out the eigenvectors? We need to solve this system of linear homogeneous equations, right? This. So corresponding, there is only one lambda. So let me just find out. So it will be like 0, 0, 0, I think 1, 0, 1, 0, 0, 0, 0, 0, 0. Okay. As you can see, like I think 2 rows are already 0. So you can just swap these 2 rows first and can make this as a pivot element. So let me just do it. 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. So if this is, let's say this is x, this is y, this is z. So what are the free variables? Y and z, right? And what are the pivot elements? X. So can you just find out? So like x is the pivot element. Then I can say that x plus z equal to 0, and let me just say that y equal to k1 and or maybe y equal to s and z equal to t, something like that, right? Y equal to s and z equal to t. This is s, okay, and z equal to t. So x will be minus t. So what will be x, y, z? X, y, z will be x is minus t, y is s, z is t, right? So it will be minus t s t. So this is the solution that we are getting, and now you can just see that how many. Now can you tell me how many linearly independent eigenvectors I'm getting? How many linearly independent eigenvectors I'm getting corresponding to lambda equal to 1? Corresponding to lambda equal to 1, how many linearly independent eigenvectors I'm getting? Can anyone tell me? See, corresponding to lambda equal to 1, I'm getting minus t st, right? Minus t st. So how many linearly independent eigenvectors? There are 2 linearly independent eigenvectors. Why? Because you can just rewrite it like this: s equal to 1 and t equal to 0. So you will be having this plus t equal to 1 and s equal to 0, right? So you will be having this. So there are 2 linearly independent eigenvectors that we have, right? There are 2 linearly independent eigenvectors. You can just see these 2 below entries, right? These 2 below entries. By that only you can say that there are these eigenvectors are linearly independent, right? So there are 2 linearly independent eigenvectors, and what is the multiplicity, or like how many times it is repeating? How many times this one is repeating? 3 times, right? If it is repeating 3 times, then at most I can have 3 linearly independent eigenvectors at most, but here I'm getting 2. That is okay. Okay, so at most I can have 3 linearly independent eigenvectors, but here I'm getting 2. Is this okay to everyone? So if it is repeating 2 times, as I said, like if it is repeating m times, as I said here, if it is repeating m times, then at most m and linearly independent eigenvectors I have, right? Here it is repeating 2 times. Here it is repeating 2 times. So I can have at most 2. So here it is repeating 3 times. I can have at most 3, but I'm getting 2 only. That's okay. Okay. So corresponding to lambda equal to 1, I'm getting 2 linearly independent eigenvectors. Okay. Okay, let's just solve this. Let's just have more questions. So let's just solve this. So you can find out a minus lambda equal to 0, determinant of that equal to 0. So what it will be? I think it will be 1 minus lambda 0, 0, 0, 1 minus lambda 0, 0, 0, 1 minus lambda, right? If you just find the determinant to be 0, then you will just say that 1 minus lambda whole cube equal to 0. Again, you are getting lambda equal to 1, 1, 1, 1, right? Now, can you find out the eigenvector corresponding to lambda equal to 1? There is only one eigenvalue which is repeating 3 times. So you can just see that a minus like you just need to find out the system of homogeneous equations. So actually a minus lambda is just 0, 0, 0, right? So 0, 0, 0, 0, 0, 0, 0, 0, 0, and 0, 0, 0, right? So how many free variables I have here? How many free variables? If this is x, y, z, so I can say that I have 3 free variables, right? So x, y, z, I have 3 free variables. Let me just name them s, t, s, t, p. So s, t, what should be the, like, what is the good name? Good alphabet should be w maybe. Okay. So actually, I remember in ISC, there is one professor called Charanjit Bhattacharya, Chiru sir. We call him Chiru sir. So like when he teaches machine learning, so he used to have all the alphabets on the board. Like there are so many equations, so many here and there, and then literally like almost every alphabet is there as a variable name. then he just get confused that which alphabet is left to use. And then usually his famous question to ask is that, okay, tell me an alphabet which I haven't used in this board. So then we just figure out, okay, you have not used this X or something. So his famous question is that, tell me an alphabet which I haven't used. Like in the middle of the class, he used to ask this question. So anyway, so STW, let's suppose, then we can just say that S into 100 plus T into 010 plus W into 001. Okay. So how many linearly independent eigenvectors I'm getting corresponding to this lambda? Corresponding to this lambda, I'm getting 3 linearly independent eigenvectors. Why? Because this is repeating 3 times, so I can get at most 3. I can get at most 3, but I'm getting 3. That's okay. Okay. Earlier it was repeating 3 times. I was getting 2. That's okay. But here I'm getting 3. That's again okay, right? So see, if it is repeating 3 times, I can get at most 3 linearly independent eigenvectors. Okay. So here I'm getting 3. Earlier I was getting just 2, and I think in some of the examples I was only getting 1, right? So okay, I'm not going to solve this. You can solve this as a homework, or should we do it quickly? How many questions I have? I have 2-3 questions. So okay, let me just do it quickly. A minus lambda equal to 0. Let's just find out. Can you tell me what are the eigenvalues? 1 minus lambda 1 0 0 1 minus lambda 1 0 0 1 minus lambda, right? This is again lambda minus 1 whole cube equal to 0, right? So again lambda equal to 1 1 1. So you can see that a minus lambda I into x equal to 0. So how to solve this? I will be having 0 1 0 0 0 1 0 0 0, and this is 0 0 0, right? And then I will be having like I can say that what are the free variables and pivot variables. So I think this is already in row reduced form. So this is the pivot variable, this is a pivot variable, right? So what are the free variables here? If this is x, this is y, this is z, then what are the free variables? I think x is free variable. So let me just take that to be k, and z will be just 0, right? Z will be just 0 using this equation, and again y will again be 0. So what is your answer? Your answer is, I think, k00, right? So how many linearly independent eigenvectors I'm getting corresponding to this lambda? Corresponding to this lambda, how many linearly independent eigenvectors I'm getting? Only one, right? Only one. So basically, see, this is repeating 3 times. I'm getting only one linearly independent eigenvector. Earlier it was repeating. Again, I'm saying it is repeating 3 times. I'm getting 3. It is repeating 3 times. I'm getting 2. So that's what I like. I think that's why I have taken these 3 examples. So it does not mean that if it is repeating 3 times, I will always get 3. Okay, and I will never get more than 3. I may get at most 3, either 2, either 3, or either 1, right? Anyway, you can solve this question. I'm not going to solve this. So just find out the eigenvalues and eigenvector as a homework. Okay. Similarly, you can solve this question. Okay. So let's just move to very interesting ideas. So till now we have seen that how to find out the eigenvalues, how to find out the corresponding eigenvector. So finding out the corresponding eigenvector is very easy. How to find out the corresponding eigenvector? Let me just write down the steps here. So step 1, you can say that what are we doing? We are solving this equation, right? This is characteristics equation. We are solving this to find out eigenvalues, right? And as a step 2, what we are doing? We are solving homogeneous system of homogeneous equation for each lambda, right? For each lambda. I mean, this a minus lambda, if it is lambda 1, so a minus lambda 1 I, this is a matrix into x equal to 0. We are solving this system of linear homogeneous equations, right? This has to have a non-trivial solution, because the way we have constructed this a minus lambda I, lambda 1 I is basically this determinant is 0, right? This determinant is 0. That's why this has to have the non-trivial solution, which means you will be able to find the x which is non-zero, and which will be your eigenvector. So for x is eigenvector, right? So this is how we are doing. Now like from this you should be able to solve like 95% of gate questions. Like I mean, they will be just asking you to find out the eigenvalues and eigenvectors, but sometimes they ask little more things that we are going to study today. Okay, so there is one more theorem that is related to symmetric matrix. So what the theorem says, so basically we have seen that if eigenvalues are repeating, then we may or may not have independent eigenvectors, right? If it is repeating three times, then we may have only two linearly independent eigenvector, only one linearly independent eigenvector, like that, right? So tell me, if none of the eigenvalue is repeating, okay, if none of the eigenvalue is repeating, then tell me how many, for a n by n, how many linearly independent eigenvectors you have. Tell me. If none of the eigenvector is repeating, then not Rahul, not at least n, because in Rn you can have only like at most n actually. So how many linearly independent eigenvectors we have? We have, since none of the eigenvalue is repeating, I can say that lambda 1 is not equal to lambda 2 is not equal to lambda 3, like that, right? Is not equal to lambda n, right? So there are n eigenvalues at most. Like there are exactly n eigenvalues if you consider this polynomial equation, which is in the degree n, right? So the polynomial equation, the characteristic of polynomial equation is always in the degree n. So it will be something lambda n plus minus, or something like lambda n minus 1. So it will be some coefficient c1 plus minus something like c2 lambda n power n minus 2. So basically the polynomial equation will be in the degree n. So that's why it has to have the n roots, right? It has to have n roots. Now the roots may repeat, may not repeat. Suppose it is not repeating. If every of the eigenvalue is different, then we know from the earlier theorem that if lambda 1 is not equal to lambda 2, and so suppose this is e1, suppose corresponding to this is e2, suppose corresponding to lambda 3, this is e3, corresponding to lambda n, this is en. So we know from the earlier theorem that if none of the eigenvalues is repeating, then ei's are linearly independent, right? And we have already proved this. As I like I'm again saying, like, the proof is not important, but the result is very important. Okay, so I will show you one or two more theorems, and the proof is again not important. I will just show you the proof, but proof is not important, but the result is important. So we have proved it, right? We have proved it that if lambda 1 is not equal to lambda 2, then e1 and e2 are linearly dependent. But proof is not important. Now lambda 1 can have how many? Yes, lambda 1 only have one linearly independent eigenvector. Since the multiplicity of since none of the eigenvalue is repeating, so it will be lambda minus lambda 1. The polynomial will look like this: lambda minus lambda 2, lambda minus lambda 3. Like polynomial will look like this, right? Lambda minus lambda n. So none of the eigenvalue is repeating. The polynomial will look like this ultimately, simplified form, right? Since it is not repeating, it is just repeating one time. You can just say like it is repeating one time or not repeating. Then it cannot have more than one linearly independent eigenvector, right? At most it can have one, and obviously like eigenvectors are non-zero, so it has to have at least one linearly independent eigenvector, right? Like whatever eigenvector it has, it is this by itself, it is linearly independent. So it cannot have more than one. It cannot have more than one because it is repeating just one time. If it is repeating two times, then at most two linearly independent eigenvectors we can have. Okay. So anyway, like we have proved this. Now suppose eigenvalues are repeating. Suppose eigenvalues are repeating. Then what can you say about the linear dependency or independency? Then can we say we always have linearly independent eigenvectors, like n linearly independent eigenvectors? No, right? See, suppose that lambda 1 is repeating m1 times. Okay, suppose lambda 1 is repeating m1 times, lambda 2 is repeating m2 times, something like that, right? And lambda n is repeating mn times. Like I'm just taking like this, where m1 plus m2 plus mn is actually n. So how should I write this? I think I should write like this, right? Is this okay to everyone? Right? I should write like this. Now I can say that at most I can have m1 linearly independent eigenvectors from here. At most, this is at most, right? At most m1 linearly independent eigenvectors here. At most, again at most, okay? At most m2 linearly independent eigenvectors from here. Similarly, at most mn linearly independent eigenvectors from here, right? So since m1, like since this is polynomial in polynomial of degree n, so can I say that m1 plus m2 plus mn equal to 0? Sorry, n, because this is the polynomial in degree n. Why it is polynomial in degree n? Why it is polynomial in degree n? Because I'm solving this. See, this is nothing but a minus lambda I, determinant of a minus lambda I. So this will be some a1 minus lambda 1, a2 minus lambda sorry, a1 minus lambda, a2 minus lambda, something like that. So there will be at most n term which will be multiplying like this, right? So you cannot have more than you cannot multiply more than n lambdas. So you can like to find this determinant, you will be having at most lambda power n. So this is basically polynomial in degree n, right? Polynomial in degree n. So anyway, here it is polynomial in degree n. So I can say that if lambda 1 is repeating m1 times, then I can rewrite it like this. But again, like m1 plus m2 plus mn just n, right? Because this is polynomial in degree n. That's why all this powers should sum up to n. Because this is because like lambda power n, like we have lambda power n, right? As a one of the term here. So that's why all this coefficients, all this power should sum up to n. So anyway, like if you can have at most m1 here, at most m2 here, so combinedly, since m1 plus m2 plus mn is n, combinedly you can say at most you can have n, at most n linearly independent eigenvectors, right? So what does this at most linearly independent eigenvectors means? Like if eigenvalues are repeating, then I can say I may have, then I may or may not have n linearly independent eigenvectors, right? Okay, it is not like I do not have. I may have. Like one of the example, if you remember, here we had 3 linearly independent eigenvectors corresponding to this identity matrix, right? So I think this example. So in this example, we had 3 linearly independent eigenvectors, and this is 3 cross 3. So we may have 3 linearly independent eigenvectors, like even though the eigenvalues are repeating, right? So we may or may not have. It's not like we do not have. We may or may not have. That's the thing, right? We may or may not have. So I hope you got this point, right? If eigenvalues are repeating, then we may or may not have. But we are interested in something else, which says that what is the condition under which that we will have n independent eigenvectors even with the repeating eigenvalues. Okay, means that in other words, are there matrices which will always have n independent eigenvectors irrespective whether the eigenvalues are repeating or not? Then yes, there are matrices called symmetric matrices which always have n independent eigenvectors. Okay, even though your eigenvalues are repeating. You got it? So basically, real symmetric eigen, if I just talk about this real, if I take this real into also account, then real symmetric matrices have two properties, that it has like these matrices has n real eigenvalues. Okay, maybe repeating. I mean, these has basically repeating like n real eigenvalues, or eigenvalues may repeat, but all the eigenvalues are real basically. Like I mean to say this. So if the matrix is real symmetric matrix, like see, one of the matrix we have seen earlier, which was skew symmetric. I think the matrix was this, right? This was the matrix. Even though the matrix was real, but the eigenvalues were imaginary, right? Eigenvalues were imaginary, even though matrix was real. But In case of real symmetric matrix, if you have real, if the value entries are real, then you will always have real eigenvalues only. Okay, you will never have imaginary eigenvalues. Okay, so for some of the matrix, as we have seen in the previous example, for some of the matrix, even though the eigenvalues are real, but the even though the entries were real, but the eigenvalues were coming out to be imaginary. But in case of real symmetric matrix, you always have real eigenvalues. Okay, maybe repeating. Okay, maybe repeating. And this is very important. Actually, this is extremely important, and we will prove both of this property quickly. But proof is again not important. And in the gate, they have asked the direct questions from the result, and result is important basically. Okay, so this is the second property is very important, that you have an independent, even like not just independent, and orthogonal eigenvector. So orthogonal eigenvectors are always independent, right? You can't get one out of another, right? If these two are orthogonal, you can't just multiply this with and you can't get this, right? And you can also prove it, right? If it is orthogonal, then this is independent, right? So anyway, like, okay, I will show you how to prove it, but these are the two properties, that real symmetric matrices always have real eigenvalues. Okay, maybe repeating, always have real eigenvalues. That's important. Let me just remove this n. Maybe you are getting confused with this n. So always have real eigenvalues, maybe repeating. That's okay. Like, it may repeat. I'm not saying it won't repeat. It may repeat, but it always have real eigenvalues. And this is important, that whatever eigenvector that you get there, even though the eigenvalues are repeating, the eigenvectors that you get, that always linearly independent. Okay, so see, in some of the cases eigenvalues were repeating, but we were having only two linearly independent eigenvectors. It is repeating three times. Even though like it is repeating three times, I'm getting only two linearly independent eigenvectors. But in the case of symmetric matrix, it is not the case. If it is repeating three times, if the multiplicity, the power is 3, if this power is 3, then you will always have, corresponding to lambda 1, you will always have three independent eigenvectors. Okay, so let's just prove this. Let's just prove both of this. So proof is again not important, but let's just quickly go through that. So first proof is that all eigenvalues of real symmetric matrices are real. So real symmetric matrices have real eigenvalues. Okay, let's just prove this. Let me start with ax equal to lambda x. Do you remember how I went about proving lambda 1 is equal to not equal to lambda 2, then e1 and e2 are linearly independent? You remember? Like, maybe you vaguely remember that I started with c1 plus c2 equal to 0. Then I said, like, okay, first multiply lambda 1, or maybe multiply with a, then you are having two equations, and then just compare these two equations, and then finally we get c1 and c2 equal to 0, right? Remember this, like some sketch of this? Similarly, like in these proofs, actually, like I will be doing the almost same thing. I will be basically starting with one equation. I will be interpreting this one equation into two ways, and I will just compare both of the ways. Okay, like the similar proof that we have done here. Let me just quickly go through the proof of this. So basically, let's suppose you start with ax equal to lambda x, where a is your symmetric matrix, not just symmetric matrix, it is real symmetric matrix, right? So a is your real symmetric matrix. So if you, let's suppose if you conjugate this a, then you will be getting a only. Why? Because it is real. There is no imaginary part, so there is no conjugation. Suppose you take the transpose of this, then again you will be getting a. Why? Because this is symmetric, and this is why, because this is real. So basically, since this is real, so even if you take the conjugate, you will be getting the same matrix. Even if you take the transpose, you will be getting the same matrix. Is this okay to everyone? Like, this is given that this is real symmetric matrix, right? I want to prove that eigenvalues of this are real. Okay, let me just quickly prove this. So see, again I'm saying that eigenvalues need not to be real if for any random matrix which is real matrix. We have already seen one example, right? So for this matrix, the since the matrix is real, but the eigenvalues are coming out to be imaginary. But in case of symmetric case, it is not the case. In case of symmetric, if the eigenvalues are real, then if the matrix is real, then you will be having the real eigenvalues only. So let's just prove this. Let me start with ax equal to lambda x, and let's just try to get x. So this is basically x is eigenvector, and this is conjugate of x, and this is transpose of that eigenvector. Okay, let's just try to get x conjugate transpose ax from this. So one of the way is to get that if you want to come up with this x bar transpose, then you can just multiply x bar transpose with the both side. So if you just do it, so you can, right, you can just do like this. So you can just multiply, I mean the pre-multiply you can get, you can do the pre-multiply, and you will be getting, like on the left side you will be getting this quantity, on the right side you will be getting this quantity. Is this okay to everyone? Let me know if there is any doubt here, like how we are getting this. You're just multiplying this quantity on both sides, right? That is very easy. Now there is one more way you can get it, get this x bar transpose ax from this. What is that way? You can first take the conjugate, okay, both side, take the conjugate both side. So it will be, right, if you take the conjugate both side, it will be like this. But you know that this a conjugate is just a, right, because this is real matrix. Now you don't know whether it is like this eigenvector is real or not, so let's just keep it x bar. You don't know eigenvalue is real or not, so let's just keep it x bar, and like this. Okay, is this okay to everyone? So how I got this? How I got this equation? Taking the conjugate both side, right? Taking the conjugate both side. Conjugate. This is how I got this equation. And from here to here, how I got, like since this a is a real matrix, that's why I can just write instead of a bar, I can just write a. Okay. And let's take the transpose both side, and I will be getting ax this transpose equal to lambda x this transpose, right? Let's take the transpose both side, and since we know that from the transpose property, I can just rewrite like this. Since lambda is scalar, doesn't matter you take the transpose or not, like 2 transpose is just 2. Since this is scalar, it doesn't matter like you take the transpose or not. So transpose of a scalar is just a scalar only, so it doesn't matter. So you can take this outside without taking the transpose, or you can, if you are very much like, then you can just put the transpose here, but it doesn't make any sense because this is scalar, right? So it doesn't make any sense to put the transpose. It is just that is scalar only. So yeah, it is this quantity. So basically what I did, I took the conjugate both side, and then I took the transpose both side, and I got this equation. And since this A transpose is just A, right? This A transpose is just A. So let me just rewrite like this. Now I want to get this quantity. Now can you tell me from here, how can I get this quantity? Can you tell me? Like I want to get x bar transpose ax. I have x bar transpose a. I can multiply with what quantity to get this x bar transpose ax. I have x bar transpose a. I can multiply with x both side, right? Post multiply. So you just multiply with x. Now you multiply with x both side. Then you will be getting x bar transpose ax equal to lambda x, right? So this is what you are getting. And the similar quantity you got from here by just simply multiplying x bar transpose both sides. So since both of the quantities are equal, you can say that this quantity which is basically lambda x bar transpose x, this quantity, right? This quantity is equal to this quantity, because LHS is equal, then RHS has to be equal, right? And this is possible only when like lambda equal to lambda bar, right? I mean this is equal to this, which means it is possible only when lambda is real, which means the eigenvalues has to be real. Okay, so all eigenvalues of real symmetric matrices are real. Anyway, like I'm not going to iterate through this proof again. If you get it, that's okay. If you do not get it, that's also okay. But our result is important. Like we want to, like, just remember this, like if you have real symmetric matrix, if the entries of the real symmetric matrix is real, then you are always going to get real eigenvalues. Okay, you're never going to get complex eigenvalues. That's what result is important. And proof is also not tough. Like proof is just like you started with this equation and you got this by two ways, right? You just get this by multiplying x bar transpose directly, or just by taking three steps. Okay, if you just directly multiply, then you will be getting this x bar transpose ax equal to x bar transpose lambda x, right? Since lambda is a scalar, you can write it in between, you can write it here, you can write it here, you can write it anywhere. It is just a scalar. Okay, you can write it anywhere. So it is just lambda x bar transpose x, right? So this is how you are getting from this if you directly multiply. But if you take these three steps, then I think we got something like this. If you take just these three steps, then I think we got something like this, right? So by comparing these two equations, by comparing this equation and this equation, you can say that this right hand side, like since the LHS is equal, so RHS is also equal, right? And from here you can say lambda equal to lambda bar, which means lambda is real. That is only possible when lambda is real. Okay. So anyway, like proof is not tough, but you do not need to remember this step. Like you need to do this, do this. You do not need to remember. I just showed you proof because that was just a small proof. But you need to remember the result that all eigenvalues of real symmetric matrices are real. Okay. Now let's go to the another property. The another property is that if we have real symmetric matrix, then the eigenvectors are always linearly independent. In fact, they are orthogonal. Okay, this is very, very important. See, like in machine learning, we use the symmetric matrices, like somehow, like by luck or like by mathematical convenience, we always get the symmetric matrices to work with in most of the cases, basically. And once we get the symmetric matrices, then like if we want to work with the eigenvectors or something, then we always have very good set of eigenvectors which are orthogonal. So that's why this property is extremely important when you go to machine learning. So this real symmetric matrix has and orthogonal eigenvectors. Okay, so let's just quickly prove this. All eigenvectors of real symmetric matrix are orthogonal to each other. Like basically they're independent. Like orthogonal means like linearly independent also, right? So how to prove this? Again, like I will start with okay, let me just do it here. I will start with let's suppose this quantity, and what I'm doing, I'm multiplying this quantity with E1 transpose. Okay, so again I'm saying let me quickly prove it, but proof is not much important, but let me just prove it. So basically I'm interpreting this quantity with two ways. You can put bracket anywhere, right? So I'm interpreting this quantity with two ways, like this. So this quantity is equal to this quantity also, this quantity also, right? So this means AE2 means what? Lambda E2, right? Since E2 is an eigenvector, like E1 E2 are eigenvectors. Okay, E1 is the eigenvector corresponding to lambda 1, E2 is the eigenvector corresponding to lambda 2. Okay, E2 is the eigenvector corresponding to lambda 2, E1 is the eigenvector corresponding to lambda 1. And since the eigen values may repeat, which means lambda 1 may be equal to lambda 2 or lambda 1 may not be equal to lambda 2. Okay, eigenvalues may repeat. In this case, symmetric case, eigenvalues may repeat, but my claim is irrespective whether eigenvalues are repeating or not, I always have E1, E2 as linearly independent. I don't care whether lambda 1 is equal to lambda 2 or not. Okay, like this is the property of symmetric matrix. In symmetric matrix, whether lambda 1 equal to lambda 2 or lambda 1 is not equal to lambda 2 doesn't matter, that E1 and E2 are always linearly independent. Okay, so so basically there are two cases. First case is lambda 1 is not equal to lambda 2. Second case is lambda 1 equal to lambda 2. So let me first take this case, which is let me just first assume that lambda 1 is not equal to lambda 2. Then I will show you that E1 and E2 are linearly independent. Then there will be a second case where we will say that lambda 1 is equal to lambda 2, and then we need to prove that E1 and E2 are still linearly independent. Okay, let's first go to this case, which is very easy. Like this case is easy. So in this, like this is the case one where I'm assuming lambda 1 is not equal to lambda 2. Okay, now you started with this quantity, you just interpret this quantity in two ways, and here you know that AE2 is just like, since E2 is the eigenvector and E1 is the eigenvector, so AE1 is lambda 1 E1, AE2 is lambda 2 E2, right? Because these are the eigenvectors corresponding to lambda 1 and lambda 2. So AE2 is lambda 2 E2, right? Is this okay to everyone? Let me know if you have any doubt till this point. Let me just stop here. I think like I'm not getting any response. So let me just ask you if you have any doubt. See, like what I'm doing, I'm just starting with one quantity and I'm just interpreting this quantity in two ways. Okay. And then we will see that if we are able to come up with something. And that's how like every textbook prove it, prove it. Like basically I'm trying to make it very easy. Like even if you read any textbook, like you may find it little complicated, but this is the simplest proof like I can come up with. Like I have searched a lot and this is the simplest proof that we can do to prove that eigenvectors of symmetric matrix are orthogonal to each other. So anyway, let's start with this quantity. So I'm interpreting this quantity in two ways. In first way, I'm saying that let me put the bracket with the AE2. So AE2 is lambda to E2. That's okay. Now here, let me just write it like this. This is A transpose E1 transpose E2, right? I can rewrite like this, right? Because if you open this transpose, then it will be E1 transpose A. So this A transpose is just, since this is a symmetric matrix, this will be A, right? This will be A only, since this is a symmetric matrix, because this is a symmetric matrix, right? This A1 is lambda 1 E1 whole transpose E2. So it will be lambda 1 transpose doesn't make any sense because it is scalar. So you can just write it lambda 1 E1 transpose E2. So you got lambda 1 E1 transpose E2 from here. And from here you got lambda 2. So lambda 2 is scalar. You can write it here, you can write it here, you can write it here, anywhere you can write it. So here you got lambda 2 E1 transpose E2, right? So I have interpreted this quantity in two ways. In one of the way I am getting lambda 1 E1 transpose E2. In one of the way I am getting lambda 2 E2 E1 transpose E2. Since these both are equal to this original quantity, then these both has to be same, right? These both has to be equal. Is this okay to everyone? Since I'm starting with one quantity, one of the way I got this, one of the way I got this. Since the original quantity is same, like this is equal to the original quantity, which is E1 transpose AE2. This is also equal to E1 transpose AE2, right? These both are equal to E1 transpose AE2. That's why these both has to be equal. Which means what? If these both are equal, then I can say that lambda 1 E1 transpose E2 equal to lambda 2 E1 transpose E2, right? Because both are equal. Then you can just take the E1 transpose E2 common, then it will be lambda 1 minus lambda 2 E1 transpose E2, right? Equal to 0. Is this okay till this point? Is this okay? Since I'm saying that lambda 1 is not equal to lambda 2, this is the case 1. So that's why I can say that this is non-zero. I can bring that to 0. So I will come up with this E1 transpose E2 equal to 0, which means E1 and E2 are orthogonal. Okay. Let me know if there is any doubt. So basically what we did, we started with some quantity, just interpreted this quantity in two ways, and then I'm saying that E1 and E2 are orthogonal. Okay. So this is the case 1. And case 2 will be case where lambda 1 is equal to lambda 2. Still I need to show that E1 and E2 are orthogonal. And this is very complicated case actually. Like this, like first case is very easy, second case is very complicated, and we are skipping this. Like I'm not going to prove for this case, like it is not even required for gate. So we are skipping this proof. So let's take this theorem as the words. So even this proof is not important. So you just need to remember that all eigenvectors of real symmetric matrix are orthogonal to each other. Okay. So yeah, this is the case where lambda 1 is not equal to lambda 2, and the case 2 where lambda 1 equal to lambda 2 is very complicated, and we are skipping this. Okay, is very complicated. But still we need to prove in the case 2 that if lambda 1 is equal to lambda 2, then also E1 and E2 are orthogonal. But it is very complicated case, so I'm skipping this. But I hope this first case is clear to everyone. Like I'm just interpreting this quantity in two ways, and I'm just saying that this is one interpretation, this is second interpretation, and this one interpretation is saying this is equal to lambda 2 E1 transpose E2, and the second interpretation is saying that this is lambda 1 E1 transpose E2, right? And both has to be same. That means E1 transpose E2 has to be 0. That's all. Okay. So this has been asked in gate. like this theorem, not the proof, but the result has been asked in gate. So let me know if you have any doubt in the proof itself. Since we are spending time, so we need to make sure that you properly get the proof. Is this okay? Like, is there any doubt in the proof, or at least this is okay? See, I don't know like why you are suspecting too much about this. This is very common thing. Like if you do the masters, then seriously, this is just seriously I'm saying this is 2 minute task for professor. They will not take more than 2 minutes to just say like to state these proofs and all. So you should be like a bit active while I'm having any mathematical proof. So I hope that is okay, right? Or let me know if there is any doubt. Like I'm quickly repeating, I just started with this quantity. Interpret this quantity in two ways. Like you can put bracket here, you can put bracket here, you can put bracket here or here. And if you put bracket here, you are coming up with this quantity, you are coming with this quantity. And since both quantities are just equal to the original quantity, that's why you can say that lambda 1 minus lambda 2 into e1 transpose e2 equal to 0. And since lambda 1 is not equal to lambda 2, that's why e1 transpose e2 has to be 0, which means e1 and e2 are orthogonal. Okay, so let's take a break. And before the break, let me just tell you what we have done till now. So till now, we have done two theorems which are important. One theorem was that if lambda 1 is not equal to lambda 2, then the corresponding eigenvectors e1 and e2 are linearly independent, right? So if lambda 1 and lambda 2 are distinct, lambda 1 is not equal to lambda 2, then the corresponding eigenvectors e1 and e2 are linearly independent. This is we have already done in yesterday's class, right? I mean, like previous class. This is we have already done in previous class. This is we have done today. That for real symmetric matrix, I always have real eigenvalues, and also this is the first thing, and also I always have orthogonal eigenvectors. It doesn't matter whether the eigenvalues are repeating or not. It does not matter at all. I always have orthogonal eigenvectors and real eigenvalues. Okay. So both theorems are important. Both theorems are very important. Now, now we will talk about the multiplicity after the break. So let's take a break for 10 minutes and let's meet at 8:36. Okay. Hi everyone. Yeah, so let's start. So I was talking about the multiplicity, right? So basically, there are two definitions. One is called geometric multiplicity, and another one is called algebraic multiplicity. So that is defined for every eigenvalue lambda. Okay. So suppose lambda one is one eigenvalue, then if I have some equation like some characteristic equation, something like this, lambda minus lambda one की power 3 into lambda minus lambda 2 power 4 equal to 0, something like this I have. Then how many times lambda 1 is repeating? 3 times, right? So this is called algebraic multiplicity, right? Number of times lambda is repeating. So here algebraic multiplicity of lambda 1 is 3, right? And algebraic multiplicity of lambda 2 is 4. Now what is geometric multiplicity? Geometric multiplicity says that if it is repeating 3 times, then the number of basically it does not matter like how many times it is repeating. It just says that number of linearly independent eigenvectors corresponding to lambda 1, right? So it may be 1, it may be 2, it may be at most 3. So number of linearly independent eigenvectors corresponding to this lambda. So corresponding to lambda 1, how many independent eigenvectors I have? Number of linearly independent eigenvectors, right? Lambda for every lambda it is defined. Now as without any proof I'm saying this, like proof is little not in the gate scope. So without any proof I'm saying this geometric multiplicity is less than equal to algebraic multiplicity, which means if the power is 3, then at most you can have 3 linearly independent eigenvectors. If power is 4, then at most you can have 4 linearly independent eigenvectors. Okay. So number of linearly independent eigenvectors is called geometric multiplicity, and the power is called algebraic multiplicity. How many times it is repeating. So I hope that is fine. Let's solve some of the questions. If number of free variables in a minus lambda 1 I x equal to 0 are 2. So basically this is a system of homogeneous equations, right? Homogeneous equations. Now they are saying the number of free variables here. Number of free variables. If you solve this, the number of free variables, they are saying there are 2. There are 2 free variables, right? So maybe something like this, and maybe let's suppose that this is a free variable, this is a free variable, and maybe this is a free variable. So number of free variables are 2. Then what is the geometric multiplicity of lambda 1? Tell me. If number of free variables are 2, then you know that in the solution you will be having something like this. You will be having something like this. If number of free variables are 2, you will be having something like this, which means you will be having 2 linearly independent eigenvectors, right? Then what is geometric multiplicity? It is just 2, because geometric multiplicity is number of linearly independent eigenvectors corresponding to this lambda 1. So geometric multiplicity of lambda 1 will be just 2. Why? Because in the solution you will be having this kind of solution, and this kind of solution means like you will be having 2 linearly independent eigenvectors. That's why geometric multiplicity is just 2. Is this clear to everyone? Right? See, here I'm solving this equation. In this equation, if I'm getting 2 free variables, it means like I will be getting this kind of solution. It means I will be getting 2 linearly independent eigenvectors. It means like geometric multiplicity of lambda 1 is just 2. Okay. Let's solve this question. Just let me know what is the answer. If A is 5 cross 5 matrix and the rank of lambda A minus lambda 1 I is just 2, then tell me what is the geometric multiplicity of lambda 1. It is 3, right? Why? Because if rank of A minus lambda I is 2, which means if you solve A minus lambda 1 I into x equal to 0, if you solve this, then you will be having 3 free variables, right? Because rank is 2, so 2 pivot variables, let's suppose this is pivot, 2 pivot variables and 3 free variables you will be having, right? 3 free variables. Let's suppose these are the free variables. free variables, right? 3 free variables you will be having. It means you will be having solution something like this, right? You will be having solution something like this, which means you have 3 linearly independent eigenvectors, which means 3 linearly independent eigenvectors. Okay, EV means eigenvector, which means geometric multiplicity of lambda 1. Let me just write it. Geometric multiplicity of lambda 1 is just 3, right? Okay, let's solve this question. They are saying that let A be 5 cross 5 matrix and one of the eigenvalue of A is 0. Okay, it is given that one of the eigenvalue of A is 0, which means, what does this mean? Okay, before I read the question further, let's just see what does this mean. That one of the eigenvalue of A is 0 means what? That Ax equal to lambda x is like eigenvalue equation, eigenvector equation. So if one of the eigenvalue is 0, then you can say that Ax equal to 0. You can put the lambda 0 and you can have x equal to 0, which means what? Like, what does this mean if one of the eigenvalue is 0? Actually 0 is very special eigenvalue. Can anyone tell me what does this mean? Can you say about like rank of A, at least, like some, like, what can you say about rank of A? If A is 5 cross 5, then you can definitely say that, see, if eigenvalue is 0, listen here, see, if eigenvalue is 0, then Ax equal to 0 must have some non-zero solution. See, if eigenvalue is 0, then Ax equal to 0, in this Ax equal to 0, X is eigenvector, right? X is eigenvector and lambda is eigenvalue, right? See, if you are putting lambda equal to 0, then you will be having X equal to 0 where X is eigenvector, and eigenvector cannot be 0. Eigenvector cannot be 0, which means X equal to 0 has some non-trivial solution. If one of the eigenvalue is 0, then do you understand that I can say that Ax equal to 0 has X as eigenvector. I mean, like, I'm writing a bit informally, but that's okay. Okay, it means what? That X is non-zero, right? Because this is eigenvector. It means what? That Ax equal to 0 has some non-trivial solution. Okay. which means yeah, columns are linearly dependent, which means rank is less than n, okay? Which means this. So if they are asking about the rank of A, then it is definitely less than 5. It is definitely less than 5, strictly less than 5, right? Okay, they've also given some more information. They are saying that it is also known that that there are 4 linearly independent vectors corresponding to 0 eigenvalue. Okay, so they are saying that 4 linearly independent vectors corresponding to 0 eigenvalue, which means what? That if you solve this A minus lambda 1 x into A minus lambda 1 I into x equal to 0, if you solve this equation, so here lambda 1 is actually 0, like eigenvalue is 0. So if you solve this Ax equal to 0, this equation, then how many free variables you have? How many free variables you have? How many free variables you have here? If they are saying that 4 linearly independent eigenvectors you have, so how many free variables you have? 4, right? See, free variables are like okay, let me just tell you once again. See here, if you have A minus lambda 1 x lambda 1 I into x equal to 0, this equation, right? This is set of equations. I say that free variables are 3 free variables. Okay, 3 free variables. Then what does this mean? Then this x will be summation of 3 linearly independent eigenvectors, isn't it? Right, as to you. Similarly, I am saying that 4 linearly independent eigenvectors you have, which means you must have 4 free variables, right? You must be having 4 free variables. Then only you can get 4 linearly independent eigenvectors like this, right? You must be having 4 free variables, which means what? 4 free variables of what? Like of which matrix? See here, like there are two matrices. There are always two matrices that we will be dealing. One is A, okay? Like basically there is only, or like always one matrix, this matrix that we will be dealing in case of eigenvalues and eigenvectors, like A minus lambda 1 I, like that, okay? There will be always one matrix, but like let me just call this matrix A1, okay? Let me just call this matrix A1. There will be always one type of matrix, and this is not equal to A, okay? So whatever they say about A1, like we will solve questions, so don't worry, but whatever they say about A1, that won't lead us to anything about the A. A is completely different matrix and A minus lambda is completely different matrix, okay? A is completely different matrix and A minus lambda I is completely different matrix. But when both of the matrices are same, I mean when A minus lambda I and A both will be same. Can anyone tell me? See, in case of eigenvalue, eigenvector, we will always be dealing with A minus lambda I, okay? A minus lambda I. This matrix we will be dealing with. They say that, okay, there are 4 free variables or something, whatever they say, then we won't be able to directly interpret this A, okay? But if they say that this matrix is corresponding to lambda equal to 0, then they are talking about A. Then they are talking about A, okay? So they are saying that you have 4 free variables. In which matrix you have 4 free variables? A minus lambda I, right? And here lambda is 0, which means in A you have 4 free variables. In A you have 4 free variables, which means what? Like if A is 5 cross 5, then which means one pivot variable. Then what will be the rank of A? What will the rank of A? 1, right? 1 is answer. You got it, or should I repeat it again? See what they are saying, or I think we have more questions. So let me just do couple of questions. I think after that it should be more clear. Let's just do couple of more questions. They are saying that let's just do this question, or maybe let me just quickly repeat what it did say, what it just said. They are saying that lambda equal to 0 is one of the eigenvalue, okay? One of the eigenvalue. Whenever they say lambda equal to 0 is one of the eigenvalue, this is very special. This is very special eigenvalue. This tells many things about just A, because A minus lambda is just A in case of lambda equal to 0. That's why it is very special, okay? Otherwise A minus lambda is some different matrix and A is some different matrix. So suppose they are saying that A lambda equal to 0 is one of the eigenvalue, and they are saying that geometric multiplicity of lambda equal to 0 is 4, which means corresponding to lambda equal to 0, you have 4 linearly independent eigenvectors, right? 4 linearly independent eigenvectors corresponding to lambda equal to 0. Geometric multiplicity is 4. That's what they are saying, right? Then it means what? It means it is only possible when you solve this A minus lambda I into X, this set of equations you solve into X equal to 0, and you have 4 free variables, then only you can get 4 linearly independent vectors, right? So basically this is just Ax equal to 0 corresponding to lambda equal to 0. So here you have 4 free variables, right? Here you have 4 free variables. Then only you can get corresponding to lambda equal to 0, you can get 4 linearly independent eigenvectors, right? When you have 4 free variables. Then they are asking about the rank of A. If it is 5 cross 5, then how many pivot variables you have? Only one pivot variable. That means rank of A is just 1. Is this okay to everyone? So basically, whenever they say about lambda equal to 0, that is very special, that they are actually talking about A. Okay. Whenever they say lambda is not 0, they are talking about different matrix which is not at all related with A. I mean, like we will see some examples, but we can't directly interpret anything about A just by looking at A minus lambda I. A minus lambda I, this matrix is entirely different from A. These two becomes equal when lambda is equal to 0. So lambda equal to 0 means they are talking about A only. Okay. So let's just do more questions. Let A be 5 cross 5 matrix and it has 4 linearly independent vectors. Okay. So okay, one thing you note here, that they are saying 4 linearly independent vectors. have they talked about anything about like whether it is corresponding to lambda equal to 0, or maybe these four linearly independent vectors, maybe these four linearly independent vectors corresponding to two different or three different or maybe four different eigenvalues, right? They are not even saying that these four linearly independent vectors are corresponding to only just eigenvalue. They are saying there are four linearly independent vectors in total. Maybe all are corresponding to one eigenvalue. Maybe all are corresponding to two eigenvalue. Maybe all are corresponding to three eigenvalue. Maybe all are corresponding to four eigenvalues. Can they all are corresponding to five eigenvalues? Can you have five different eigenvalues and just four linearly independent eigenvectors? Five different eigenvalues and you just have four linearly independent eigenvectors? Can you have this? Can you have five different eigenvalues and you have four linearly independent eigenvectors? No, right? No, we cannot have, because if lambda 1 is not equal to lambda 2, we have already seen if lambda 1 is not equal to lambda 2, then even it was linearly independent, right? We have seen that is theorem 1. So basically, if these are not equal, then you have E1, E2, E3, E4, E5, both are like all are linearly independent. You have five. You have basically total you have five linearly independent vectors, right? Not just four. Is this okay to everyone? So basically, like they have just in this question, if I only talk about this question, they have given that you have four linearly independent vectors, maybe corresponding to lambda 1, maybe corresponding to lambda 1, lambda 2, maybe corresponding to lambda 1, lambda 2, lambda 3, maybe corresponding to lambda 1, lambda 2, lambda 3, and lambda 4, right? So now they are saying about what is the rank of A. Okay, basically they are asking that what are the free variables or the pivot variables in the Ax equal to 0 or something like that, right? Ax equal to 0. Suppose they say that these are the four linearly independent eigenvectors corresponding to lambda equal to 0. Corresponding to lambda equal to 0. They say this, they're corresponding to lambda equal to 0. Which means that A minus lambda I into x, suppose they are saying that corresponding to lambda equal to 0. Which means that you solve this, if you put lambda equal to 0, you solve this, you have in this A, you have four free variables, right? If they say that these are the four linearly independent eigenvectors corresponding to lambda equal to 0, then four free variables, right? And one pivot variable. Is this okay to everyone? If they say that corresponding to lambda equal to 0, then what will the rank? Rank will be just 1, that we have just seen, right? Right? That we have just seen. Rank will be 1. So, but now they are not telling me that it is corresponding to lambda equal to 0 or not. Right? They are not telling me anything about the lambda equal to 0 node. So what can I say about the rank? I don't know actually. Right? Not enough information. Not enough information. I cannot say about the rank. If they only talk about lambda equal to 0, then only I can comment. Okay. See, we will always talk about A minus lambda I, which is not same as A. Which is not same as it. This is some different matrix. This is some different matrix. If lambda equal to 0, both get same. Okay. If they just say that four linearly independent eigenvectors, I do not know. I do not know whether it is like what is the rank of this A. Maybe 5. Maybe less than 5. I do not know actually. Okay. If they say that okay, this is corresponding to lambda equal to 0, then only I can comment. Okay. I hope that is fine. Let me solve more questions. Okay. Just tell me if this is true or false. Inverse of a matrix does not exist if and only if matrix has 0 eigenvalue. See, if matrix has 0 eigenvalue, then what does this mean? Ax equal to lambda x, right? Then what does this mean? That you have Ax equal to 0 has non-trivial solution, which means A columns of A are linearly dependent. Is this okay to everyone? If 0 is eigenvalue, then columns of A are linearly dependent, isn't it? If columns of A are linearly dependent, which means determinant has to be 0, right? Then can inverse exist? If determinant is 0, then can inverse exist? No, right? So inverse does not exist. Yes, so does not exist. Yes, this is true. Okay, this is true. Rajan, we have seen this. We have also seen this. Like there were cases where I think we have 3 by 3 matrix, right? 3 by 3 matrix, and we just had two linearly independent eigenvectors, right? Two linearly independent eigenvectors, and in those cases, like we have seen that the rank of A was 3. So basically, in case of 5 cross 5, if they do not talk about that whether the eigenvalue is 0 or not, then we can't comment about the rank. If they do not talk about the whether eigenvalue is 0 or not, okay. If they say that eigenvalue is 0, then you can talk about the rank. Otherwise, there is no relation between the rank of A and the number of linearly independent eigenvectors. Okay, there is no relation between the rank of a matrix and number of linearly independent eigenvectors. If they say that eigenvalue is 0, then we can only talk about. If they do not reveal the eigenvalue is 0 or not, then we can't say anything. There is no relation. Okay. Okay, let's just solve this. A matrix of size 5 cross 5 has only two linearly independent eigenvectors. Then it must have repeated eigenvalues. Then they are saying that there is a matrix of 5 cross 5 and it has only two linearly independent eigenvectors. Okay, let's suppose E1 and E2. Then it must have repeated eigenvalues. Suppose it do not have repeated eigenvalues, then what? Suppose every eigenvalue is different. Suppose every eigenvalue is different. Suppose it does not have repeated eigenvalues. Every eigenvalue is different. Okay. Suppose every eigenvalue is different. Then there will be five linearly independent eigenvectors, right? 5 linearly independent eigenvectors that we know. 5 linearly independent eigenvectors. But they are saying that you have only 2 linearly independent eigenvectors. Then yes, you must repeat eigenvalues. You must repeat eigenvalues. You cannot have distinct eigenvalues. Then this is true or false? This is true, right? You cannot have distinct eigenvalues, because if you have distinct eigenvalues, you must have 5 linearly independent eigenvectors, but you only have two linearly independent eigenvectors, right? That is given. So you must have repeated eigenvalues. Okay. Is this okay to everyone? I hope that is fine. So let's solve this question. Let A be 15 cross 15 matrix and one of the eigenvalue is 0. Yeah, this is interesting. See, whenever they say one of the eigenvalue is 0, then they will talk about, instead of A minus lambda I, they may talk about the A only. Okay. Then what is the rank of A? One of the eigenvalue is 0, which means that Ax equal to lambda x, if one of the eigenvalue is 0, basically Ax equal to 0 has non-trivial solution. Yes, very good, Rahul. Non-trivial solution, right? Which means the rank of A, I cannot tell the exact value, but it means like it is definitely less than 15. Definitely less than 15, because determinant of A has to be 0, right? Because columns of A are linearly dependent and determinant of A has to be 0, rank has to be less than 15. I cannot tell the exact value, but yeah, rank has to be less than 15. Okay. Okay, now they have modified the question a little bit. They are saying that one of its eigenvalue is 0. It is also known that 10 linearly independent eigenvectors are there. Okay, for A. So they are saying that one of the eigenvalue is 0, and they are saying that 10 linearly independent eigenvectors are also present. Then what is the rank of A? See, they have not given that these 10 linearly independent eigenvectors are corresponding to eigenvalue 0 or not. Okay. If they are not revealing me that these are corresponding to eigenvalue 0 or not, then I cannot say about the exact relation about the rank. Okay. Again, rank is less than 15, because this information is not helping me anything, because they are not revealing me anything about the 10, whether this 10 is related to eigenvalue 0 or not. Okay. So let me just modify this question a little bit, and let's suppose they have given this question, and I will come back to that question again. Okay, let me just read out this question. They are saying that one of this eigenvalue is 0. It is also known that the 10 linearly independent vectors of A are there, and out of which they are saying that 4 linearly independent corresponding to 0 eigenvalue. This is important. Now tell me, what is the rank? See, they are saying that four linearly independent eigenvectors are there corresponding to 0 eigenvalue, which means you have 4 free variables in A, right? 4 free variables in A. Then how many pivot variables in A? In A, right? In A, not in A minus lambda I, because A is exactly equal to A minus lambda I if the eigenvalue is 0. So how many pivot variables are there? 11 pivot variables are there. If 11 pivot variables are there, 11 pivot variables are there, then what will the rank of A? You will just say the rank is 11, right? Rank is 11. So here you can tell the exact answer, because they are revealing that how many eigenvectors are based on this zero eigenvalue, right? If they are not revealing me, if they are just saying that 10 linearly independent eigenvectors, they are not revealing whether out of 10 how many are like all 10 or 9 or 8 or 7, something like that. They are not revealing, then it won't help me anything. It won't help me to find the rank. Okay, I will just say that rank is less than 15 because it is giving that eigenvalue 0. Okay, so I hope that is fine. Like like now you know that if you know the if you know the eigenvalue is 0 or not, then only you can talk about the rank. Otherwise there is no relation between the eigenvectors or these and the rank. Okay, if you know that eigenvalue is 0, then only you can talk about the rank. Okay, and you know that eigenvalue is 0 and how many linearly independent eigenvectors are there corresponding to a 0 eigenvalue, then only you can talk about the rank. Okay, let me frame one more question. Like suppose A is a matrix, rank is taken after eigenvalue 0. After eigenvalue 0 means like rank is defined for A, like I mean rank is defined for a matrix A, and if they are saying that eigenvalue 0 has some independent eigenvectors, let's suppose 4 independent eigenvectors, this means that A minus lambda I into x equal to 0. If you solve this, you will be having four free variables, and this is nothing but A. Here you have benefit. You can directly say that this is nothing but A. That's where you have benefit. We can't have more rank. We can't have more rank. No, more rank means like if this is let's suppose 15 cross 15, then at most you can have 15 pivot variables. Then 15 is rank. At most 15 rank is possible. So rank is unique. Like rank is defined for a matrix. Rank is unique. And if you have, let's suppose, I think your confusion is that if you have eigenvalue lambda 1 which is not 0 1, then what will the rank of A? Right? What will the rank of A? So rank of A is fixed. Rank of A is fixed. Rank of A is fixed. Right? But if you have lambda equal to 0, then you are able to calculate the rank with this help, with the given information. That's what I'm saying. You are able to calculate the rank if one of the eigenvalue is 0. Yes, Amar, we can say if again I'm saying if eigenvalue is not 0, you can't comment anything about the rank. You don't know. There is no relation between rank and eigenvalues. I mean non-zero eigenvalues basically. Okay. There is no relation. There is no relation. If the eigenvalue is 0, then you will talk about the rank and all. Okay. Rank of A and all. Yes, very good, Amar. So because for non-zero eigenvalue, this is the different matrix, right? For non-zero eigenvalue, this is a different matrix. This is not A, and this is not related with A. This is a completely different matrix. This is completely different matrix. Rank may entirely change for both of them. Okay, rank may entirely change. That's the reason. Okay, so I was asking one question. Let's say that A is one matrix and which is having some nullity. A is a matrix of, let's suppose, 10 cross 10 with nullity 5. Okay, with nullity 5. Then my question is, what are the my question is basically, what do we have? First question is that, do we have 0 as eigenvalue? Zero is eigenvalue. And my second question is, if yes, then how many let me take it 4. Okay, nullity is 4. If yes, then how many linearly independent eigenvectors are there? How many? Or let me just ask in simple way. If yes, then what is the geometric multiplicity of 0? Okay, let's solve this question. So just try to solve this question. Let me know what is the answer you are getting. Nullity is given as 4, which means what? Like which means that you have 4 free variables, right? 4 free variables. Yes. So it means that you have 4 free variables. 4 free variables, right? Which means that in ax equal to 0, in ax equal to 0, you have 4 free variables, which means that your solution will look like this. Since your solution is consisting for ax equal to 0, since your solution is consisting some non-zero vector, which means this ax equal to 0, this corresponding to the eigenvector of 0 eigenvalue. If this is non-zero, then this is the eigenvector of 0 eigenvalue, right? If this is 0, like I mean, if you do not have any non-trivial solution, then yes, if this is 0, you cannot say this is eigenvector because this is not defined. Like 0 vectors are not eigenvector. But if this is non-zero, then you can always say that that x is eigenvector corresponding to the 0 eigenvalue, right? Corresponding to 0 eigenvalue. If this is non-zero, and they are saying nullity is 4, which means you have some x like this, which is non-zero, right? So you can say that yeah, there are 4 linearly independent eigenvectors. I mean, there are 4 linearly independent vectors which are forming the solution of x, and this is non-zero. So x is a valid eigenvector. So do we have 0 as eigenvalue? Then yes. And if yes, then what is the geometric multiplicity? Which means geometric multiplicity means that if you solve this, a minus lambda I into x equal to 0, if you solve this, then what will be the linearly independent vectors for this x? Like for this lambda, which is 0, what will the linearly independent vectors? Like what are the number of solutions? So as we know that there are 4 linearly independent vectors, so I will say the geometric multiplicity is just 4, right? Just 4. Have you got it? Like, see, whenever they say that 0 eigenvalue, okay, then everything is just related to ax equal to 0. Then they may talk about nullity, they may talk about rank, okay, they may talk about nullity, they may talk about rank, they may talk about anything. See, I have given some nullity or something, right? They may say rank, like they may talk about something like anything. If they are saying 0 eigenvalue, if they are saying non-zero eigenvalue, then there is no relation between rank or nullity of a, like nullity of a and some non-zero eigenvalue, right? So whenever they say 0 eigenvalue, then you should immediately think about ax equal to 0. Just what I'm saying. Yes, you can't comment anything. Can't comment about rank. Okay. Whenever they say non-zero eigenvalue, then with this help you can't comment about rank. But whenever they say 0 eigenvalue, with this help you can comment about rank or nullity or something. Okay. So let's move to a very simple 2 more properties, and I'm just calling it magical properties. Okay. So there are 2 very important properties of the eigenvalues, which are as follows. So one property says that determinant of any matrix is product of its eigenvalues. Okay. So suppose suppose lambda 1, lambda 2, lambda 3, there are three eigenvalues, then determinant of A is just lambda 1 into lambda 2 into lambda 3. Okay. Now tell me, if one of the eigenvalue is 0, then what is the determinant? What is the determinant? 0, right? If the one of the eigenvalue is 0, then determinant is 0. And we have already seen with the another like kind of argument that one of the eigenvalue is 0, then we can say that Ax equal to 0 has non-trivial solution. Then we can say that columns are linearly dependent. Then we can say that determinant is 0. But we can also say that if one of the eigenvalue is 0, then determinant is 0. Why? Because determinant is just a product of lambda, these lambdas, right? If one of the eigenvalue is 0, then determinant is 0. We can definitely say like this, right? So actually there are multiple ways in the linear algebra to interpret the things. Okay, so this is one property. Second property says that trace is some of the elements along the main diagonal. Okay, and here we have the square matrices in this complete chapter. So this is the main diagonal, and like there will be always a square matrix, right? So trace some of the elements is the of a matrix is some of the eigenvalues. So let's suppose that this is A11, this is A22, this is A33. Then A11 plus A22 plus A33 is just lambda 1 plus lambda 2 plus lambda 3. Okay. Let's just quickly prove it for 2 by 2. Okay, these two properties. Let's just take 2 by 2 matrix and let's just see if this holds. So what is the determinant of this? What I'm going to do? Yeah. So A minus lambda into D minus lambda minus BC, right? Equal to 0. So if you just simplify this, it should be lambda square and minus lambda coefficient will be D minus D and minus A, right? A plus D lambda minus BC equal to 0, right? You can simplify like this. Now, in the quadratic equations, if you have ax square plus bx plus c equal to 0, then do you remember what is the sum of the roots and product of the roots in the quadratic equation? Sum of the roots are, I think, minus b upon a, and product of the roots is c upon a, right? So here you can say that if you have two eigenvalues, which is lambda 1 and lambda 2, then lambda 1 plus lambda 2 will be minus b, which is a plus d upon a is just 1. A is 1 or? Yeah, a is 1, right? Okay. So lambda 1 into lambda 2, it is minus bc, right? Now tell me, isn't it the for the matrix A, B, C, D, isn't this lambda 1 plus lambda 2 is a trace? This is a trace, right? Trace, because as you just see here, this is a trace. A plus D, right? And is this the determinant? This is not determinant, right? So determinant of A, B, C, D is AD minus BC. Okay, I forgot one term here. It should be AD also. 1 second. So yeah, this is determinant, right? So basically, I have just shown you 2 by 2, and this is generalized. Like you can say that for any matrix, it is not just 2 for 2 by 2. The determinant is a product of eigenvalues, and sum of the eigenvalues is basically the trace of that matrix. Okay. Now let's just solve this. If the columns of matrix are linearly dependent, then one of the eigenvalue has to be 0. Tell me this. If the columns of matrix are linearly dependent, which means what? This determinant is 0. Determinant is 0, right? If the columns of matrix are linearly independent, determinant is 0 possible only when, since determinant is the product of eigenvalues, right? Product of eigenvalues. The determinant 0 is possible only when one of the eigenvalues is 0. Otherwise, determinant 0 is not possible. How can the positive or negative quantities multiplying together could be 0 if none of them is 0, right? So that is why one of the eigenvalue has to be 0. Why? Because determinant is 0, then one of the eigenvalue has to be 0. So this is true. Okay. The trace property shows that if eigenvalues are imaginary. So Rahul, we will take this little later. Okay. So we will take your question little later. So let me just complete one or two things, and then we will talk about it. I will take your question. So let's go to one of the. Okay, you figured out. Okay, so let's go to one of the lemma. It is very easy. It says that if lambda is eigenvalue, if lambda is eigenvalue, then lambda conjugate is also eigenvalue. Okay, which means if if 2 is eigenvalue, then 2 conjugate is just 2. 2 is also eigenvalue. That's okay. I mean that is not adding any information. But if in like it makes sense in case of complex case, if iota or I is eigenvalue, or I plus 1 is eigenvalue, then the conjugate of this is minus I plus 1. This is also eigenvalue. This is what they're saying. Okay. So how to prove it? That's very easy. Ax equal to lambda x. Let's suppose Ax equal to lambda x, where x is eigenvector, lambda is eigenvalue. Take the conjugate both sides. Right? Now they are saying that A is having real coefficients, which means this A conjugate is just A. And you don't know about eigenvector, that's okay. Equal to, you don't know about the eigenvalue, whether it is like conjugate or not. So that's okay, right? So you started with this and you got this. So from this equation, what can you say about the eigenvector and eigenvalues of A? Eigenvector of A will be x conjugate, and eigenvalue of A is lambda conjugate, right? And we started with eigenvector here, like if we are given that eigenvector of A is x, and eigenvector and eigenvalue are x and lambda. Okay, if we have x and lambda, then x conjugate and lambda conjugate are also eigenvector and eigenvalue. Okay, I hope that is okay to everyone. That we can just take the conjugate, and A has to be the real matrix, real coefficients. Okay, A has to be real coefficients. Now let's do this question. They are saying that let A be the 5 cross 5 matrix. There are exactly 2 linearly independent vectors corresponding to eigenvalue 0. Then what will the rank of it? That is very easy. You can just tell me quickly. 3, right? Why? Because they are saying that Ax equal to 0 has solution in which you have 2 linearly independent eigenvectors, right? 2 linearly independent eigenvectors, which means like nullity. You can say nullity of the free variables is 2, then rank has to be 3, right? Rank has to be 3. This is nullity, or you can say free variables. This is rank, or you can say pivot variables, right? Okay. Let's do this question. They are saying that there is one matrix. Do you remember like what kind of matrices they are? Like, I mean, like if you remember me saying that these are rank 1 matrices, right? These are called rank 1 matrices, basically. Rank 1 matrices. Anyway, so they have given you some matrix like this, and then they are saying that what is the largest eigenvalue of this? So let's just do the product first. This means 1 to 1 to, right? You can quickly do it. Like basically this means like 1 time of first column and 1 time of this again first column. So this is 1 to 1. Now you can find out the eigenvalue and eigenvectors in the usual way, but like can you do it by just looking at the matrix? What should be the largest eigenvalue? See, rank here has to be 0, right? I mean determinant here has to be 0. Why? Because these are linearly dependent. That's why determinant has to be 0. It means one of the eigenvalue has to be 0. Then only determine 0 possible, right? One of the eigenvalue has to be 0. Then only determine 0 possible. And and since it is 2 by 2 matrix, there could be two, like there cannot be more than two eigenvalues, right? So if one of the eigenvalue is 0, what will be the another eigenvalues? Yes, this is just trace. By just looking at the trace, you can say that lambda 1 plus lambda 2 is just 3, and one of the eigenvalue, which is lambda 1, which is 0. So 0 plus lambda 2 is equal to 3. Then you can say lambda 2 is equal to, right? Or you can just find out the eigenvalues and eigenvectors in usual way also. That's not a problem. Okay, so let's do this question. This question is a bit special, and let me just read out this question. They are saying that suppose A is n cross n matrix having n linearly independent eigenvectors. Okay, so A may be symmetric matrix, may not be symmetric matrix. Basically, if it is symmetric matrix, then you know that it has linearly independent eigenvectors, right? You know this, right? If A is symmetric matrix, then we always have n linearly independent, in fact, n orthogonal eigenvectors. And orthogonal, like orthogonal eigenvectors are obviously linearly independent, but yeah, like more, more than like if I put more information, then you can say that n orthogonal eigenvectors, right? And orthogonal eigenvectors you have in case of symmetric matrix. But if it is not symmetric, then also you can have like this. That's not a problem. If it is not symmetric, then also you can have an orthogonal and linearly independent eigenvectors like this. Okay. So A, be a random matrix, and they are saying that they are having n linearly independent eigenvectors. Okay, that's good. Now, S be another matrix having eigenvectors as column vectors. I mean, S is like this. So eigenvectors, suppose there are n eigenvectors which are linearly independent. This is important because it is given to us. So n linearly independent eigenvectors, they put them as in column vectors. Now they are saying, can you just simplify this AS, which means A into S? How A into S will look like? So this is some A, this is some S, right? Which look like this. So this is S, this is A. Now, if you want to simplify this, do you remember how we have multiplied two matrices like in another way, like one of the usual way, but some other way you remember? So what I have done, I have said, like, this column you can take the coefficients from this column, and then you can have the linear summation of these columns, right? And the coefficient will be coming from this column. You remember, right? So basically if this is A and this is, let's suppose, E1, E2, E3, so I can say that this product is nothing but like A1, which is just a vector, comma A2, I mean not comma, basically like these are the columns of this AS. So AE2, AE3, like this. Okay. So basically I'm multiplying this A with E1, E2, E3. So I can multiply this A, I can multiply this A with E1, then this will be a one column. I can multiply this A with E2, this will be another column. So I can write this AS like this. I can write this AS equal to this is E1, right? So I can write this as AE1. So you can multiply this A just like this, A into E1, and then A into E2, like this, AEN. Okay. Is this okay to everyone? Basically, given any matrix, given two matrices, basically, you can do in whatever way you want to multiply. Like you can treat this matrix as a column matrix, which means, okay, let me just treat this as a row matrix first. Let's say this is row 1, okay, row 2, like vector, like I have written like this, but in fact it is just R1, R2, R3, where R1, R2, R3 are row vectors, right? And let's say this is C1, C2, C3, something like this. Okay, so these are the column vectors. So you can just say that this is C1, C2, C3. So basically I have written this matrix, these two matrices, in the compact form. Okay, R1 is one row, one entire vector, R2 is one entire vector, R3 is one entire vector, but I have written in the compact form. Similarly, I have written this C1, C2, C3 in the compact form. So now you can say this, just treat them as a scalar. Just treat them as a scalar. R1 as a scalar and C1 as a scalar. Like just for the sake of understanding, just treat them as a scalar. So R1, and you can just say that it is nothing but R1 into C1, which is a dot product, R1 into C2, R1 into C3, just treat them as a scalar. Similarly, R2 into C1, R2 into C2, R2 into C3, like that. I mean, you can write two matrices in the compact form like this. Anyway, like whatever way you like. Maybe if you like to write first matrix as a column matrix, another matrix as a row matrix, then also you can do it. So basically, you can say this is C1, this is C2, this is C3, right? This is R1, this is R2, this is R3. Then it will be basically C1, C2, C3, right? R1, R2, R3. Now basically, like you need to keep the dimensions correctly, but you can treat them as a scalar. So it will be C1 R1 plus C2 R2 plus C3 R3, right? Basically, you can write in the compact form. It will be C1 R1 plus C1 R2 plus C3 R3. And in fact, like the C1 R1 is one matrix, C2 R2 is another matrix, C3 R3 is another matrix. But anyway, that's okay. This is summation of three matrices. Basically, you can write two matrices multiplication in the compact form also. So, like in fact, you can write if these are the two matrices, you can say that, let's suppose this is row 1, okay, this is row 2, this is row 3. Let's suppose these. Then you can just say that, okay, let me just write this whole matrix as a compact form A. Then what it will be? It just treat them as a scalar. So it will be A into R1, A into R2, A into R3. Right? But you need to keep the dimensions, like you need to take care of the dimensions. Similarly, you can you can do the compact representation of this. This is A, this is C1, this is C2, this is C3. Then you can just say these multiplication is just A into C1, okay, A into C2, A into C3. Okay. So anyway, like you can multiply matrices in the compact form also. So just treat this A as just one scalar, and you can just write A into E1, A into E2. This is a valid multiplication. There is no problem. So what is A into E1? Can anyone tell me? If E1 is eigenvector, can I just say that A into E1 is the lambda 1 E1? I can say, right? So basically, A is one matrix that was given to me. S is another matrix that they have said like S is one matrix such that S is having eigenvectors as a column vectors. That is given to me. Then they are saying just simplify this AS. Just simplify this AS. So I can say that let me just simplify this AE1, AE2, AE3 like this. Okay. Then I can say that see, this AE1 is just lambda 1 E1. This is just lambda 2 E2. Okay, this is just lambda 3 E3. Okay, like that. Now if in that case you can say that, okay, like you have almost simplified this AS, but let me do it little bit more. Okay, so AS is coming out to be like this. Is this okay to everyone? Like how we are multiplying two matrices. So you can just multiply this A with every column and you will get columns like this. Then can you also rewrite like this? This is E1, this is E2, this is E3. Can you also rewrite like this? Lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. See here, can you also rewrite like this? See, like if you multiply these two, are you getting this? Let me just quickly check. This is saying the first column will be you will be getting by lambda 1 into first column plus 0 into second column plus 0 into third column. That will be lambda 1 E1. Yes, you are getting lambda 1 E1. And similarly, you will be getting lambda 2 E2 by 0 into first column plus lambda 2 into second column plus 0 into third column. You will be getting lambda 2 into E2. Right? So basically, you have simplified AS into this form. Now, you are just saying that AS equal to, so actually this is a bit special, that's why I'm simplifying it again and again. AS equal to, this is just S into, let me just call this matrix as capital lambda, okay, capital lambda. So this is AS equal to S lambda. That's how we are simplifying this, right? AS is just S lambda. Now, since the eigenvectors are linearly independent, that is given to me in the question, that eigenvectors, there are n linearly independent eigenvectors, that means S inverse exists, right? S inverse exists because these are linearly independent columns. That's why S inverse exists. Since S inverse exists, I can just multiply with the S inverse both sides, and then I will be getting this. Since S inverse exists, otherwise I can't do it. So A is finally this, where S is what? S is the eigenvectors E1, E2, E3, right? And this capital lambda is eigenvalues, lambda 1, lambda 2, lambda 3. And this S inverse is just like inverse of this eigenvector matrix, right? Is this okay? Like how I'm simplifying this A into, you are doing A into S, it will be A into S is given to me like this. Then you are doing A into E1, A into E3, A into E2, A into E3. Then you got lambda 1 E1, lambda 2 E2, lambda 2 E3. Then I'm saying that I can rewrite it like this. Then let me just take this matrix as a capital lambda, and then you are getting AS equal to S lambda. Then you will be getting A equal to S lambda. Since S inverse exists, because it is given to me that that these eigenvectors are linearly independent, that's why S inverse exists. So I can say that A equal to S lambda S inverse, right? So basically, any matrix A can be written in this form. If S inverse exists. Which means what? Which means like if you have n linearly independent eigenvectors, then only S inverse exists, right? Because S is just all the eigenvectors. S is just all the eigenvectors. Yes, non-singular, right? If S inverse exists, then you can write a matrix A like this. If you have, for any matrix, if you have n linearly independent eigenvectors, then you can write that matrix in this form. That is actually called diagonalization of matrix. Diagonalization. Okay, that is called diagonalization. Anyway, like they have asked just one time in one of the option in the gate, but I just showed you that it is not very tough. Like you can just multiply A into S, and you will be getting S lambda. Basically, AX equal to lambda X, that you know, right? AX equal to lambda X, that you know. And this is just one eigenvector. And instead of taking one eigenvector, can you take the set of eigenvector? Then can you say AS equal to lambda X? Here you have the capital lambda, but that's all, right? Instead of just one eigenvector, you can take all set of eigenvectors. If the all set of eigenvectors are linearly independent, then you can also multiply by the S inverse. Okay. So anyway, like any matrix which is having n linearly independent eigenvectors can be written in this form. What is the benefit of this? What is the benefit of writing this? Actually, taking power is very easy. Like if you just take, let's suppose you can write a matrix like this. Then you take, let's suppose a cube. Let me just start with a square. Taking power is very easy in this form. So you will just say a square is just this. 2 times multiplication of this. Then this will be identity. Then this will be just S. And this is diagonal matrix. So finding power of the diagonal matrix is very easy, right? This is a diagonal matrix, and finding power of diagonal matrix is very easy. So this is lambda square S inverse. So finding power of a square, like A, is very easy. Like if you want to find the power of a 100, then you can just say like this. Why? Because like if you keep on doing this, then this matrix, like a square is coming out to be like this. Similarly, a cube will come out to be like this. So finding power is very easy in that case. Extremely easy. You just need to take the power of this scalars, because diagonal matrix finding power is easy, right? So that is why. If Amar is asking if n linearly independent eigenvector exists, then we can write a completely based on its eigenvector and eigenvalue. Yes. That is actually called eigenvalue decomposition. And like obviously this is not important for gate, but in machine learning there is called singular value decomposition. That even allowed us for rectangular matrices, and these decompositions are very important for machine learning. So anyway, so in from the gate point of view, you only need to understand this, that if A is given to you, then if you are having n linearly independent eigenvectors, so can you simplify this AS? So yes, you can do it. A into S will be like this. A into S is this. So A even, so you can just simplify like this. So very easy. Should be able to do it, right? Should be able to do it. So you can write A like this. A equal to S lambda S inverse. So this is like, this should be done from gate point of view. Okay. Yes, Amar, like we can do it. There is nothing fancy here. You can just multiply this matrix with the another matrix like this, and you can just rewrite matrices. Okay. So let's do another question. And anyway, like not the question, sorry. So there is one more theorem that is very easy theorem that says that if you have any characteristics polynomial, okay, like how to find out the characteristics polynomial a minus lambda I determinant is 0, right? This is how we find out the characteristics polynomial. Then they say that let's suppose this is the polynomial is lambda, which means like this could be lambda power n plus c1 some coefficient into lambda power n minus 1 plus c2 some coefficient into lambda power n minus 2, something like this, right? C n minus 1 or something like this. Like cn lambda power 0 or constant, some constant. So you have some polynomial in lambda which is called characteristics polynomial. Then this polynomial is also satisfied by your matrix, which means you can also say that a power n plus c1 a power n minus 1 like this plus dot dot dot, at last you have cn, but since you are dealing with the matrices, so you need to multiply with the identity matrix. Okay, so let's just do one example. Suppose a is one matrix, then what will the characteristics polynomial? So you can find the determinant of a minus lambda I or lambda I minus a. That's okay, right? Because anyway you are going to put 0. You are going to put equal to 0. So it doesn't matter whether you say a minus lambda I or lambda I minus a, right? So both are same. So because it is just 0. So this is the characteristics polynomial that you are getting. Then this also, like your matrix also satisfy this, which means you can also say that PA equal to a square minus 5a minus 2i2. Okay, this is important, which is 0. And you can verify this, right? You can find out the a square, you can find out the 5a, and you can multiply the identity by 2. You can verify this is in fact a 0 matrix. So suppose they ask you from this they ask you what is the value of a cube minus 5a square minus 2a. What is the value of this? Then are you going to find out the a cube and then minus 5a square then 2a? No, right? You know that from the characteristics polynomial a square minus 5a minus 2i equal to 0. Then you just multiply a both sides. Then it will be a cube minus 5a square minus 2a, which is again 0, right? So it will be 0. They may ask some complex polynomial, and you should immediately think about the characteristics polynomial. They may ask some polynomial in the matrix, that a cube minus 5a square, something like this. Then you should immediately think about the polynomial, corresponding polynomial, characteristics polynomial. Replace this lambda by a, and then you will be getting the polynomial in the matrix. Okay. Okay, so let's do one more question. I think, do I have questions or I have something else? So I have questions only. So let's quickly do one or two more questions. Or should we take a break of 5 minutes and then we should do? This is 9:40. So we can quickly do, I think, or should we, let's take the break of 5 minutes, or should we continue? What do you guys say? Okay, let me continue then. I think we can continue if none of you are speaking. So let's say what is given here. If lambda is non-zero eigenvalue of AB, if lambda is non-zero eigenvalue of AB and x be eigenvector of AB, then what will be the eigenvalue of eigenvector of BA? So they are saying that AB has AB into x equal to lambda x, right? Because x is eigenvector and lambda is eigenvalue. So of AB. So AB into x equal to lambda x, that is given. Then they are asking about lambda is non-zero, basically, like why it is non-zero, like why it has to be non-zero, that I will tell you. But yeah, they are saying that lambda and x are two eigenvalues. Sorry, lambda is one eigenvalue and x is the corresponding eigenvector. Okay, so you can write like this. This is given. Now they are asking about BA. Okay, so if you multiply with the B both sides, you will be getting BA. Like if you multiply with the B both sides, BX equal to B lambda x, right? And since lambda is a scalar, you write it anywhere, doesn't matter, right? So let me write it here. Is this okay? By multiplying B, you will be getting this. Just multiply B both sides. If you multiply b, the pre-multiply if you do, then BA/BX, right, equal to b into lambda x, right? You will be getting like this. Now tell me what is the, can you just spot the eigenvector of BA? Can you tell me what is the eigenvector of BA by looking at this equation? Eigenvector of BA means BA into some vector should be lambda into some vector, same vector, right? So from here I can say eigenvector of BA is BX, right? And eigenvalue of BA is, can anyone tell me what is the eigenvalue? Lambda, right? Lambda, yes. So eigenvalue is lambda, eigenvector is BX. But is BX really eigenvector? Which means I need to verify whether BX is 0 or not, right? If it is 0, then it cannot be eigenvector. Now tell me from this equation, just by this equation, can BX be 0? If BX is 0, then this lambda x has to be 0, right? Can lambda x be 0? If x is eigenvector of some matrix, then x is not 0 and lambda be non-zero. Lambda is also non-zero. So this is non-zero. This whole thing is non-zero, right? This whole thing is non-zero. Because lambda is non-zero, x is eigenvector, that has to be non-zero. This whole thing is non-zero. That's why bx cannot be 0. If bx is 0, then this product has to be 0, right? That's why bx is non-zero. So it is a valid eigenvector. That's okay, right? So yeah. So now I'm able to find out the eigenvector and eigenvalues of BA. But the important thing is to notice here the eigenvalues are same. So I can say that if lambda is eigenvalue of AB, then the lambda is eigenvalue of BA also. This is like a very interesting result. I mean, you do not need to remember these things, but yeah, like as a question you can solve it. So if lambda is eigenvalue of AB, then I can say lambda is eigenvalue of BA, right? Is this okay to everyone? Now, is this correct statement or there is something is missing here? One little thing is missing. The lambda is not some random. Lambda has to be non-zero. Like if it is non-zero, then I am able to do the whole calculation. Then I am able to claim that this is eigenvector eigenvalue. So lambda has to be non-zero. Okay, lambda has to be non-zero. So I can say that if lambda is non-zero, non-zero eigenvalues basically, non-zero eigenvalues of AB and BA are same. Okay, non-zero eigenvalues of AB and BA are same. Now suppose there is a question that A is let's suppose 5 into 10 matrix, B is let's suppose 10 into 5 matrix. Okay, then AB will be 5 into 5, BA will be 10 into 10, right? 10 into 10. Now they say that the eigenvalues of AB, are like this: 1, 2, maybe like 3, 4, 5, let's suppose something like this. Then what will be the eigenvalues of BA? What will be the eigenvalues of BA? This has to be same, right? Non-zero has to be same. Non-zero has to be same. If it is non-zero, this has to be same. But now they are saying it is 10 into 10. It is 10 into 10, right? It is 10 into 10. So what about the other eigenvalues? So there will be lambda power 10 equation, right? Lambda power 10 equation. So what about other eigenvalues? Other eigenvalues will be 0. Other eigenvalues will be 0. Why? Because you just see in the reverse way that BA has these eigenvalues. Then AB has to share the non-zero eigenvalues. Whatever is the non-zero eigenvalues, AB has to share them. And remaining eigenvalues are 0. Okay. So basically, okay, let's do one more question. Like this is the same question basically. I have written as a statement also that repeated also has to share. So anything, if it is repeated, then it will be repeated in AB also. Repeated also has to share. So there will be only possibility is 0. So one of them will certainly have the zero eigenvalues. Okay. So A is m into n, B is n into m, and A, B, and B, A share the non-zero eigenvalues. If when m is not equal to n, then one of them will certainly have the zero eigenvalues. There will be remaining eigenvalues will be zero. Okay. So let's solve this question. Tell me what is the answer. If A is a matrix, and A transpose A has three eigenvalues. A transpose A has three eigenvalues, which is 490. Then what are the eigenvalues of A transpose? What is the dimension of A transpose? I think 3 cross 3, right? This is 2 cross 2. 2 cross 2. Since this is, you can treat it like A and B, this is just AB and BA. So they has to share the non-zero eigenvalues, right? So they has to share the 4 and 9. Like, and this is 2 cross 2, so that's all. Like this cannot have more than 2 eigenvalues. So what are the eigenvalues of A transpose? This is just 4 and 9. Okay, they has to share the non-zero eigenvalues. I hope that is fine. So what will be the determinant? What will be the determinant of A transpose A? It is 0, right? Why? Because one of the eigenvalue is 0. One of the eigenvalue is 0. That's why determinant has to be 0. Okay. Tell me if the eigenvalue of lambda, eigenvalue of A is lambda, then what will the eigenvalue of A power k? They are saying that eigenvalue of A is lambda. Let me take eigenvector as x, and they are saying that eigenvalue is lambda. Then what is the eigenvalue of A power k? Let me just check for A square first. Let me just multiply the A both side with the A both side, and let's just see what is happening. Okay, let's just multiply this A both side. Then it will be A square x equal to lambda into ax. Lambda is just a scalar. You can write it here between anywhere you can write it. Doesn't matter. Okay, this is equal to lambda into ax is just lambda x again. X equal to just lambda x, so it will be lambda x, which is just lambda square x. So you got that A square x equal to lambda square x. What can you say about the eigenvector and eigenvalues of A square from this equation? What is the eigenvector? Eigenvector is x, right? Because A square into some vector should be some constant into that vector itself. So that's why eigenvector is x. What is the eigenvalue? Eigenvalue of A square is lambda square, right? Eigenvalue of A square is lambda square. Why? Because you multiplied by A, then you found out that you can write A square x equal to lambda square x. That's why eigenvalue is just lambda square. Similarly, if you do it k times, then you will find out that you can also write A power kx equal to lambda power kx. Then what is the eigenvalue of A power k? It is lambda power k. Okay, what is the eigenvalue of A power k? It is lambda power k. Okay, let's find out the eigenvalues of this. If eigenvalues of A is lambda, which means Ax equal to lambda x, then what is the eigenvalue of A power k plus 3 A power k minus 1 plus identity? What is the eigenvalue of this? Whatever is the eigenvalue of this, like I should be able to write equal to lambda into x. I mean, like whatever the lambda prime, whatever the eigenvalue into x, right? I should be able to write like this. Then lambda prime is the eigenvalue, and I want to find the value of lambda prime. Is this okay to everyone? Like I want to find the value of lambda prime because like lambda prime, if the lambda prime is eigenvalue, and they are asking about the eigenvalue only, eigenvalue of this matrix, right? So you can multiply with the x. What it will be? It will be A power k into x plus 3 into A power k minus 1 into x plus x, right? You know that A power k into x is nothing but lambda power k into x, right? Because A power k has the lambda power k as eigenvalue, right? So, and x, if x is the eigenvector of A, then A power k also has the eigenvector x. That we have already seen that Ax equal to lambda, from Ax equal to lambda x, you can also say that A power k x equal to lambda power kx, right? So it will be lambda power kx plus, similarly it will be 3 into lambda power k minus 1 into x plus x, right? So you can take the x common, and whatever is remaining is lambda prime. So what is remaining? You can take the x common plus 3 lambda power k minus 1 plus 1, right, into x. So this is lambda prime. So this is the eigenvalue of this matrix. You got it? How we are finding? This is the eigenvalue of this matrix. Okay. So basically, in general, if lambda is the eigenvalue of A, then A power k has the lambda power k eigenvalue. Similarly, for any polynomial, it's not just A power k. For any polynomial, if you want to find the eigenvalue, then just put like this. Like if this is the polynomial in the matrix, then if you want to find the eigenvalue of this, then just put instead of A, just put the lambda power k plus 3, lambda power k minus 1 plus 1. This is the eigenvalue of this matrix. Okay, this is true for any polynomial. Similarly, if you want to find out the eigenvalues of let's suppose A inverse, so Ax equal to lambda x, you know. If you want to find out the eigenvalue of A inverse, so you can just multiply by the A inverse both sides. A inverse Ax equal to A inverse lambda x, right? If you just multiply by the A inverse both sides, it will be x equal to A inverse x into lambda, right? And then you can just rewrite it like this: A inverse x equal to 1 upon lambda into x. Now, from this equation, what can you say about the eigenvalue and eigenvector of A inverse? Eigenvector is x, right? Because A inverse into some vector equal to some scalar into that same vector. So that's why eigenvector is x. And eigenvalue is 1 upon lambda, right? 1 upon lambda. So what is the eigenvalue of A inverse? It is 1 upon lambda. Actually, it is true for any polynomial. Like if you want to find out the eigenvalue of A power k, it is lambda power k. If you want to find out the eigenvalue of A power k plus A power k minus 1, then it is lambda power k plus lambda power k minus 1. If you want to find out the eigenvalue of A inverse, then it is 1 upon lambda, like that, right? It is true for any power, even negative powers. Okay, even negative powers it is true. So in general, like I have written it here. If you have any polynomial, okay, any polynomial in A, let's suppose A power k plus 1, anything, A power k, anything you have, then you just put the lambda here. Then you will be having this as an eigenvalue, lambda power k. This is the eigenvalue of new matrix. So this is true for any polynomial. And yeah, we have seen for A power k specifically, we have seen this, like, but this is true for any polynomial. This is true for A inverse. This is true for any polynomial. Okay. So let's just do this last question, and I think, yeah, 1 or 2 questions we have. Let's just do these 2 questions and then we will wrap up. So this question is saying that which of the following is true about the n cross n matrix having only real eigenvalues? Okay. Very easy question. If it is having only real eigenvalues, then if the trace of the matrix is positive and the determinant of the matrix is negative, at least one of the eigenvalues negative. Obviously, determinant is negative only when at least one of the eigenvalues is negative, right? Because everything is real. You can't have iota square or something like that, right? So if the determinant is negative, then only possibility is that one of the eigenvalues is negative. So yes, this is true. This is definitely true. Okay, because otherwise determinant can't be negative, right? Trace is positive or not, that's okay, but determinant can't be negative. Like if you do not have, if you have every eigenvalue which is positive. Okay, let's see the B option. If the trace of matrix is positive, okay, all its eigenvalue has to be positive. Is this true? It is obviously not true, because like you can have -5 or something like this, like +10. Still the trace is positive and the eigenvalues is -5 and 10, right? So need not to be true. If the determinant is positive or like this, you can do it. Like these all other options are false. Very easy options, you can check that. So 2 negative eigenvalues, then also it is positive. Yes, 2 negative eigenvalues, then also it is positive. So that's why they are saying at least one, right? At least one of the eigenvalue is negative. 2 negative is okay. So in which option you are saying? So you can do it. Basically, that's very easy options. That's plus and minus. Okay, you can do it. Let me go to a good question. This is a good question. So they are saying consider matrix P whose only eigenvectors are multiple of this 1, 4. So basically, they are saying that like they are saying that this is like the eigenvectors of this. So maybe there are repeated eigenvalues or not. Are they talking about this is the eigenvector corresponding to eigenvalue 0? No, right? So can you talk about the rank? No, you cannot talk about the rank. You cannot talk about the rank. Why? Because you do not have any information about the zero eigenvalue. They are not saying about anything about the zero eigenvalue. We have seen these kind of questions. Like if they are only saying about that these are the eigenvectors or something like that, then you don't know. Like you can't say anything about the rank at least. They are saying P does not have any inverse. You do not know. Maybe rank is n, maybe rank is less than n. You do not know. May or may not be. May or may not be. May or may not. May or may not inverse, right? You do not know. Basically, if they are not saying anything about the zero eigenvalue, you cannot talk about the inverse or not. You cannot talk about the rank. Like you cannot say inverse exists or not. It depends on the rank. P has the repeated eigenvalue. Yeah, just tell me. Can P have the, okay, just look at it in the different way. Can P have the different eigenvalues? Can P have lambda 1 is not equal to lambda 2? No, right? Why? Because otherwise you will be having two independent eigenvectors, but they are only having one independent eigenvector. That's why P has to have the repeated eigenvalue. So P has to have repeated eigenvalue. So second is true. P cannot be diagonalized. Like this is also true. Diagonalized means like you need to have independent eigenvectors. Like diagonalized means like you, like as I just showed you. So A is equal to S lambda, where A equal to S lambda S inverse. Anyway, if you do not know about the diagonalization, that's okay, like no problem. But diagonalization is possible only when eigenvectors are linearly independent, because you need to have S inverse for the diagonalization. S is nothing but your eigenvectors, right? So you need to have S inverse for the diagonalization. Then only diagonalization is possible. So if you do not have the independent eigenvectors, so that's in that case diagonalization is not possible. So P cannot be diagonalized. This is true. So second and third necessarily true. So you can say that D is the answer. Second and third necessarily true. Anyway, diagonalization, don't worry about it. You can just remember one line that if the eigenvectors are linearly independent, then you can diagonalize. Okay. Let me just write it. If otherwise, don't worry about this diagonalization. Tell me a question. Can we always diagonalize symmetric matrix? Can we always diagonalize symmetric matrix? Do we always have eigenvectors linearly independent corresponding to symmetric matrix? We do have, right? Symmetric matrix eigenvectors are even orthogonal. Orthogonal eigenvectors. No, Rahul, like real symmetric matrix has real eigenvectors, but in general, symmetric matrix has orthogonal eigenvectors. Okay, so maybe conjugate, but they are orthogonal. So in like, let me just simplify this. Let's suppose we are talking about the real symmetric matrix. Let's not worry about the real or imaginary. Let's only talk about the real symmetric matrix. So can we always diagonalize real symmetric matrix? Yes, we can diagonalize because we have orthogonal eigenvectors, right? So it means we have n linearly independent eigenvectors, which means S inverse exists, right? If S inverse exists, then I can say A is equal to S lambda. I can say, and from this I can say A equal to S lambda S inverse, because S inverse exists, and S is nothing but your set of all eigenvectors. Okay. So this is all about linear algebra. I think we did a very rigorous treatment about the linear algebra. So this, like, don't think that I have taught you something extra that is not required for GATE. So everything I have taught in this course, it is required for GATE, but it's just that we do not learn it like if we like learn it from other sources. So that's why you may think that it is not required for GATE, but everything that we have learned in this course is required for GATE. So I have not obviously there is no time like we can study extra things. So we will study like after the GATE, but whatever we have studied till now, it is everything is required for GATE. Okay. So last question, this question. P has a repeated eigenvalues. This is what you are saying, Amar. This question, right? So P has the repeated eigenvalues. Suppose P do not have the repeated eigenvalues. Suppose eigenvalues are not repeated, which means they are distinct eigenvalues, lambda 1 and lambda 2. Then you must have independent even E2 which are linearly independent. You must have two linearly independent eigenvectors, right? You must have two linearly independent eigenvectors, right? And they have given that all eigenvectors are multiple of this, which means only one linearly independent eigenvector we have. Only one linearly independent eigenvector we have. Which means repeated, like distinct eigenvalues are not possible. If distinct eigenvalues means two linearly independent eigenvector you must have, but you only have one linearly independent eigenvector, that means distinct eigenvalues is not possible, which means you must need to repeat the eigenvalues. So repetition, there has to be repetition. P has the repeated eigenvalues. Distinct is not possible, right? Okay, we have actually proved this theorem, but like as I said, like proof is not important. You need to remember two results that I told you. One result is about the symmetric matrix, and another result is about like if the eigenvalues are not same, then eigenvectors are linearly independent. You need to actually, like, let me just say it. You need to remember this. Okay. Every matrix has at least one eigenvector. Every matrix has at least one eigenvector. Like eigenvectors are not one or something. Like eigenvectors are always infinite eigenvectors. Like if X is eigenvector, then basically, like it need not necessary that every matrix has one real eigenvector, as we have seen in one of the case that 0 0 I think -1 1 in this matrix. Then eigenvectors were complex, right? So you may not have the real eigenvector. For this matrix, you do not have real eigenvector. Otherwise, for imaginary case, you can definitely solve for any equation. For imaginary case, you can definitely solve for any equation. Only one eigenvalue and one linearly independent eigenvector for matrix possible. One eigenvalue, okay, lambda 1 only, and one linearly independent eigenvector. Yes, this is possible. So if this is only one eigenvalue, if it is, I think we have seen this, right? We have seen this in one of the case. I don't remember 3 2. There was one matrix, and we were having solutions like this, k into 1 0, something like this, right? We have seen this in one of the example. So there was only one eigenvalue and only one linearly independent eigenvector. Right? Is this okay, Rajan? So we have seen this in one of the example. I think one of the very first example we have. Rahul, is this clear? So for every, obviously, like if you go for the complex case, you can solve for any x and any lambda. But for every matrix, you may not have eigenvector in real sense, in real value, because this matrix is by inherently it is rotating every vector. It can't keep any vector in the same direction. So that's why you do not have any real eigenvector for this. Okay. Okay, so we will meet for the probability if we are taking it live. Otherwise, like we will see if I will record the probability lectures. So most probably we will take, most probably we will take the probability live. Then for option 2, why we can say repeating eigenvalues, one eigenvalue is possible. Yeah, so repeating eigenvalues means P has the repeated eigenvalues. See, if P do not have the repeated eigenvalues, which means if it has multiple eigenvalues which are not repeating, if it is repeating, then that's okay. If it is repeating, P has a repeating eigenvalues, yeah, that's true. I mean, you are supporting your argument, Rajan, right? So whatever we had, whatever example we had, we had the repeated eigenvalue. Let's suppose I don't remember the eigenvalue. I think it was 3. So we had the repeated eigenvalue, and we had one eigenvector only, right? So that's the same case. You have one eigenvector and you have repeated eigenvalue. So you just think in the reverse way. Like if you do not have the repeated eigenvalue, if you have the distinct eigenvalue, then you can't have only one linearly independent eigenvector. Then you must have two linearly independent eigenvector if you are having two distinct eigenvalues. Okay. You can think about it. Yes, we will take the probability live, don't worry. So we will take the probability live, and compiler and CN, I will provide the recorded lectures, and we will take the doubt session for the compiler and CN, definitely. Okay. Okay, thank you everyone. Take care. Bye bye. See you.